So, we will start with the today's schedule. So, first I am going to give the lecture on this rainfall and temperature indices analysis using rainfall and temperature indices for analyzing hydrologic extremes. So, where we will see what are the indices available and how we can, what is the fundamental understanding of those that indices. Then we will see the case studies, like cases, like we did like a myself and then Sridhar and then our scholars, we did lot of case studies, means almost 3-4 case studies which are already available in the general public domain. So, those things I will present so that you can see how the indices can be calculated, how we can analyze those things, as a basis how we can see those things. So, those things one by one we will see today. So, just like a what is the extreme indices which we are interested, which normally useful for any is extreme studies, either maybe the flood related things or drought or any other type of climate related things, we need some indices. So, what is the background of these indices and how these are important, and then some of the case studies, those things we will see one by one. So, this so what is the background of this extreme climate indices? So, normally in the initial stages, I think most of you may know, we are using something like any climate data is there. We used to do something like what is the minimum, maximum, then used to do something called drawing some curve like a either standard deviation or those things we are doing to normal distribution, we are fitting some curves and we are looking at some return periods. So, those things we are doing normally, that is normal way of understanding any of the data set. But over time, so that like a there is like a we need to know within the data set there should be something called extremes, means like which are the either side of any, if you draw any distribution or if you are having the probability of occurrence of those events, if you put them into the distribution curve, you will come to know that where those things are there really. And as we said, like ours is like not like a something occurring hydrologic process, but we are more interested in what are those extremes. It's something like we need distribution we call outliers. So, what are those things, where they are there, and what is those type of things, what is their frequency, that all things we need to understand. So, the main thing is like the frequency or severity of those events will really make us to understand how they are impacting this natural or anthropogenic systems. So, those outliers are those which are there in that curve, which are important actually. We need to analyze those things, how many times they are occurring, so what is their return periods. So, that is exactly what we are going to require, and most of the times that is like as important to analyze this extreme. So, they are all indices that are important for this extreme event analysis. So, normally we require for this calculation of these indices, we are required the daily data set. So, for example, you can ask like a monthly and annual for a large scale we take, means we can work, but what is the problem if we take the monthly or you can say the annual scale. So, any of these data sets when you are calculating the indices or later we want to analyze for extremes, why we need to go for daily resolution. So, if you go for average, means what will happen? So, it is like averaging out. So, you are taking the monthly, we are cumulating, for example, rainfall means you will take cumulative. So, temperature means you will take some average. So, we will not get the what exactly the daily variations. So, when you are calculating most of the indices, we require the daily data set. So, previously actually especially the manual, you can say the way of maintaining data, we will not use to get much of these daily data sets or very few events. So, few years only we used to get, but now because of the availability of this we are discussing yesterday, right, so many sources are there, they are making available this daily data set. That is what we are going to use for calculating these indices. So, most of the times this data at least daily basis, we do not need to have the hourly or sub-hourly like that. Daily means we can especially we can able to understand most of the climate related aspects, especially extremes we can easily analyze. So, actually this thing, that is what I am say explaining to you. This is very important, you can say graph. So, here normally what you will do, you will take any data set, you are trying to draw a, we can say distribution curve, right. So, that is one is you see on that thing what is the, you take the temperatures. So, like we can start from one end to other end temperature we can give, and we can do like a occurrence of those temperature events over the years. So, every year you take and then it will go on repeating, like that is where the probability of occurrence we can see. So, like that if you are go on draw, we can see so many normal things, they are, we see the peak time they will come as normal of temperature, but we can see the either the one of the extremes, Here the very cold temperatures, very hot temperatures. You see they are at the both end of the curve. So we are, that's what is the thing. So they will explain about our extremes actually. So the question here is how many times you can see that both ends are, they are becoming more means what? Extremes are more. So more we can say times, that is like a probability of occurrence means like a more number of times particular thing is occurring. So there we need to focus. That's where that will give the information for us. So we are going to deal with the two, not the normal remaining part. That is a normal hydrologic study. But we are studying about the either part of that curve. Okay. Similarly, when come to the, you can say the precipitation. So like a normal light rainfall and average rainfall, most of the curve will be here, probability of occurrence. But if we go for this one, we can see the heavy rainfall events. Okay. So this will become the, you can say so much. For example, this is like a more length or more times it is occurring means what? More number of events are occurring. So it is becoming, you can say, for example, this particular value becoming more up to here, for example, then what is the meaning of that one? You see it is like a less now, it is a very, y-axis it is very thin, right? It is becoming more thick means what? Occurring means like a more times of these extreme events are occurring. That's what is the more we need to focus or we need to study those things. Okay? Means what? The data set, the data which is like a 90% of the things which is there on this side, right? And 90% of the thing other side. So we are taking the other side of the 95%, means that is called actually the, they are, if you keep them in the percentile, so this is the normally come under the 90 percentile this thing on either side. So those things we need to focus about and we need to study. So 90 percentile, 95 percentile, so all those you can say tail ends. So those things we need to study. So this is the clear you can say explanation we can see in the reference. This is one of the important paper for today's discussion actually. So actually that's what I am saying. So this is all these indices which will foretells of the distribution which are going to be more relevant and more important for the extreme studies. So more extreme an event, we can see the more societal or environmental damage will be there. That's where we need to understand, that's where we need to study those things. Or their occurrence we need to analyze. Okay. So then you see like suppose we are making our own indices and somebody is making other indices. But now, most of the times now these type of studies, right, other day you are seeing and Sridhar also explained like it is all like a global scale, right, temperature variation, extremes, we will see at least like a level of, we can say the country, state, one basin or global scale. So it's like a, to bring the normality means like a, to like a, for example, if I make a study or some other person make a study, so there should be like a, some normal way of understanding about these extremes. So they come up means there is a one, you can say the background means a lot of work done like to prepare this extreme indices. So like anybody now, anybody study that type of extreme indices they want to study, so they can take these indices which are going to show right now, they can start with those things. But only thing is, for example, we are working in India means we can only, some indices are useful for us. So we are working, for example, some other countries, they are, some indices are important. So only thing is you need to check those things which are relevant for us. Okay. So here this is like a working group, this is like a climate change, you can say institute or climate variation working group is there. So they are like international level, they are making all these things, so they put all these people are across their working research, right. So they put together all those indices and they come up with a list of, you can say this one, indices. So it is like a, so many you can say people who are come together and then this is like a working group, they prepared this indices actually. So that like all those efforts are individuals that done, they come up with a finally with a few you can say the indices. This is the you can say ET CCDI. So I think if you check in the thing and then I gave the link also so that we can check. So this is called like a joint expert team on climate change detection and indices. So they made a complete list of indices and how to, for a large scale data, what is the formula for calculating those indices, how to analyze them. So all the things they prepared the systematic, we can say, documents. So they made some definitions like some people are working like they made a common definition for most of the indices. So there are 27 indices all over the things, like any extreme study you want to make. So like for example, one basin you are taking, Krishna or Godavari river basin you are taking for example. In that you can, out of these 27 indices, you see which are the indices suitable, accordingly we can analyze. So this is the what I am saying, the working group. So here we can get all these you can say indices information. So this is like you can sometime you can verify, like a lot of information is there, but I will not give all the things, but just one time you can see this what exactly this contain. This is I am saying like this group, and this is only one thing I will show you here. There is like this I am saying like indices, right? So this all the indices we will see one by one, but you can see for any more interested means you can check all these indices exactly. So like all those you can say there exactly all this you can say formula and how we can calculate, what is the definition, everything is given. So few things which I am explaining next or slides I taken important things and I gave the what is the definition, and then small you can say simple like I said like we did some case studies like a simple calculation of how those things we can do, those things we will show here. At the same time in the afternoon today all our you can say work is to do this thing only. We will take some data set and we will calculate these indices. With already we made a all complete code like a precise exact code required for these things as per these definitions. You can run those things and you can get the results. We will see those things. So now why these indices are important? So and what are the important extreme indices actually we will study. So same thing whatever I am showing in the previous thing. So just to look we divide into all these indices will come in three parts. Either we are working with the something extreme event is occurring in terms of number of days, that is like a unit day, and other is like a for example either a temperature maximum or minimum, that is like a degree centigrade, or rainfall. So means all those indices 27 indices are they are almost like a classified into only three categories. Temperature indices, something temperature, or some day, either temperature or rainfall event something occurred in a particular you can say the time, you can say duration. Then other one is like a amount of you can say the rainfall. That is the three indices. So you see that I put that color, I kept the different things to show you. So here just like you can see one indices, I think remaining all in the same way like the graph I showed you, right? If you correlate with the graph and you can see means you can get all the definitions of all the indices. Okay. For example, you can see this one. So here the I can say we will see like a wherever there is a, this is called consecutive days when the you can say the number of you can say rainfall is less than 1 mm, that is called CDD actually. So here this maximum number of consecutive days means for example this is like a you have to see like a continuously how many number of days the rainfall is less than 1 mm. So in a year you take so you have to check continuously like how many days the less than 1 mm. Those all things you have to count, that become the you can say. So for example first 3 days comes, then 4 days, all the things combined will become the for 1 year one value it will become. Like second year, third year, like for example our IMD data other day you are seeing, right, like 100 days 100 years will be there. You can get the CDD per each per 1 year. So for example that all those CDDs you kept in a you can see one graph, you will come to know what is the trend of those things. So this you are doing for 1 point, right, one grid point or one you can say gauge point. Then the same thing you can put across those basin, across those gauge points, you will come to know as a spatial term how those parameters will vary. Okay, that is our you can say main goal. Like so understanding these selecting those indices and then calculating those indices and then put them in the you can say the temporal scale and then keep them in the spatial scale. That's what is the way you can get the idea about how the extreme indices or extreme events, how they are going to occur in the a particular basin or watershed or an area. Okay. So here this is the for example I am saying about day units it will come, right. For example this you can see this one, this is like a wherever there is a total rainfall greater than 95 percentile, means if you take the value that one I saw the graph, right. So all those events in a year when they are coming more than for example this one 95 percentile those things. So those things you will accumulate and then we will take for example here. So how many times that particular 95 percentile times are coming. So those things all will make that will become this particular 95 percentile precipitation, 99 percentile precipitation. This is like a what is the extreme events which you saw in the previous graph, right, both the you can see the extreme side. Okay. Similarly the you can say this is like a only the monthly maximum 1 day precipitation, 1 day within 24 hours how many times you will see the like a in the month for example this August we are getting a lot of rainfall within that which is the maximum rainfall. So here but here only will calculate the day like how many days, like for example normally this August month, September for this area, normally we have to get the more number of rainy days, or where we can get a maximum rainfall days. That type of things you can check, that will give idea like really we are reaching that particular amount of rainfall is coming or not, otherwise any extremes are coming or not. Okay. So similarly, this is the rainfall related things, right? And the number of, these are the 4 are related to temperature. Okay. So within a month, you can see the, you can say the daily max, you can count all those like 30 values are there, right? In that you see the maximum value in the 30 for 1 month. Like that if you take 12 months means 12 value you will get. Okay. Similarly, the you can say same like in that one, so the maximum in that maximum value, maximum only in that minimum value, that will give you like what is the variations for 1 month. So like that we can make for 12 months in 1 year, right? So for example, you have data 50 years, same way you can prepare all those data sets. Then we will analyze how that variation is there, and then how the mainly we will see like what is the trend or pattern in those final, after this indices is calculating, then you will check for the trends. Okay. So these are the parameters, right? You can see the some more list of the parameters. So previously the what we see are the related to the, you can say, temperature and rainfall, right? These are the some other information it will tell more about the, especially for the extreme, you can say the, for example, these things are like a useful when you are going with a heat wave. Heat wave calculation will be there, right? Every year the heat waves will be there in the some of the places, right? So that is like that will give that annual count. For example, there is some value like a more than 25 means that is like a number of summer days in the annual count, and especially these things. So wherever there is a regions where we want to, this type of things you are checking means you can check with this number of IC days, it's less than 0 degrees centigrade, that days will be counted. So like this is counted for every year. So the all this put into the one graph, then we will come to know what is the variations. Okay. So then this is like a, previously we saw this with respect to precipitation, right? Now with respect to temperature. So this temperature also like a, what is the percentage of days when 90th percentile, that is like extremes will be there, and 10 percentile means in the middle of the things. So you can see somewhere here these things what I am saying, I think you are. So this is the one just I am showing about this place. So what and all this I am saying, anytime you remember 95 percentile means these things. So 10 percentile means this is the place from the middle like we are going either side. Okay. Same thing, this is the extreme, you are like this is the 95 percentile group. Okay, or 99 still we will extreme further. Okay. So you can see this thing just okay. So now you saw the indices, right? There are very simple definitions, right? This is like a very simple, like the only thing is we need to check all these, you can see the indices. Okay. So when you are explaining case studies, like you can see simple one particular thing is like how we can calculate also you can see. So those things you will check how these indices will be really calculated after analyzing those indices, and how we can put together as a, you can say, temporal and spatial scale, and how we can analyze them after calculating those things. So those things we can see one by one now. So this is one case study. So as we did for the, as Sridhar and myself and then all other scholars, actually this is a Spark project. So is one of the objective is to understand the these two basins which you are going to see what is the importance of these basins. These basins like a special basins in the, you can say the Andhra Pradesh, they are there. So they are the small basins which are not having so many construction of the, you can say the dams, and they are also like a prone for the normal frequent, you can say, floods. So those things we studied, and then we saw some of these trends. You can see some of those things. Then we can get what exactly the meaning of how these trends really we can make. This is the basin I am saying about. So this thing they are called twin basins, means like a side by side. So both are directly joining to Bay of Bengal, and then these are the climate grid points. IMD grid points, already you are checking, right? So if you can click for this basin, these are the IMD grid points. Okay. So these are the basins, right? These are the all those you can see the information. So this is the main problem of this basin is like a frequent flooding. So almost twice the, you can say the year we can see the floods, like especially the monsoon season, or anyhow there is a cyclones are there, especially it is very close to Bay of Bengal, right? Whenever there is a cyclone in the Bay of Bengal, there is every chance that this region is one of the prone area which is going to be affected. And at the time these two rivers are going to get you can say floods, not other than the conventional monsoon season. Okay. So this is the, you can see, data sets, that's like especially the analysis whatever we perform, this one is the, this particular case I am explaining. So these are the two things. So the rainfall for the 110 years, that's like a 0.5 degree by 0.5 degree, and the other day some of you are asking like a temperature, it's 1 degree by 1 degree temperature sets. So these things are there, remaining all used for other further study on the same problem, but this explanation is this only. These are the things, like this is what you have to want whenever you are making extreme study, right? So there are 27 indices I said, right? So you can't, there is no logic actually. You are using, for example, if you want to calculate something like IC days I said, right? There is no logic for that particular thing to use in this particular study. Similarly, we are more interested about the number of rainy days and then extreme rainfall like that in this particular study. So there is no point in taking with other things for. So like that you need to see what type of you can say parameter you are studying, and what type of you can say the basin, where the location, accordingly you can 27 you can select the indices, and you have to, whenever you are preparing the analysis, right, you have to mention that how many indices you are selected for this study. So the all things you have to mention exactly their definitions and then unit all the things. Okay, so you can see this one. So these are like of course right now today you are all going to work, but you can see what is the way it will be done. So for just you can see like this, you are going to do, program will do for you for today, just only thing is, but you can see what is the concept, then automatically you can get what exactly how you are going to do these things. For example, here you want to calculate these extremes. So here for example you have to see the like a CDD, like we are calculating right previously, like a CDD means what, the number of consecutive days where the rainfall is less than 1 mm. For example, in this case this is like a every day is there, right? First you can see the you see the starting onwards, you can see the how many, you can say this value, can you show the, tell me the value how much it will come actually in this CDD. For this we have the 8 scale, right? For example, in this 8 numbers are there, right? So in that first like a CDD, like how many days it will come. CD means consecutive dry days, rainfall less than 1 mm. 4 days, right? That is like a one value, means like a first cycle, for example, you are taking 4 days. So then same, like this is only 8 days, like normally 1 year or 20 years like that we are going to make, and every year you are going to estimate. Sometimes what you will do, this cycle is important, like two things are there here. One is called period, other is called within the period the day. It is called actually IJ. So J means period, but like a period means like a cycle. So for example, only your study is like every monsoon you want to study. Then monsoon is 3 months, for example, then it becomes the like a whatever may be the 3 months, 3 into 30, accordingly 180. That become J become 180. Within the 180 days, every day you will verify like this, and accordingly you will accumulate or you count number of days or number of rainy days or whatever the calculation you will do like that. Every indices will be calculated like that only. So like a number of periods you are going to study, like a suppose the annual scale means every year, like a, for example 50 years you are studying, become the 50 years is the J. Within 50 years 365 days will be there, right? That become the I. Accordingly you will verify. So that's where what I am saying, like you will take the cycle. Okay, so that's that just like that's what I am telling, the number of, we can say, taking this one. So this case is the 4. So like this you are trying, right? Means like a number of years there we will not try like this, right? That's where we will tell the, you can say, program. That's where we are going to do that one today. Either in the, there are 2 programming languages I am saying, right? So either R programming language you can do very easily, and we can do Python programming, which today we are going to plan, we are plan that one for you. So you can do this calculation. So means one cycle or some just few means you can calculate, but so many are there is no point, we will not do. So automatically the program will do, but only thing is, it is calculation is going correct or not, you need to check for small data first, then you can take. Otherwise sometimes there is a, when you are writing, like normally we will take somebody's code, right? Like sometimes you will write, sometimes you will take the code. So unless you verify few things, you can't take that as a correct calculation. That you have to be careful. Okay, so that is like a, of course here the 2 things will be there in the indices calculation. One is called normal, you can say a trend, and then change point. So change point means actually the, you can see, so normal, these are once again standard. I think any of you are studying the, you can say this trend analysis or those things. So one of the statistical things we need to check is the Mann-Kendall test. So this Mann-Kendall test is like a statistical formulas are there, like once you are getting this all those CDD, everything, every extreme, every year you will get one extreme value, right? Indices you will get, right? So we will see the our temporal scale, and then accordingly in the temporal like a one grid point we are studying, you are studying for 100 years means 100 values you will get. So 100 values you will see the trend. So for the trend, whether it is increasing trend or decreasing trend or neutral trend, those things will be given by this Mann-Kendall test. So any of you can check more means like it's all like a theory, you can see the equations for this Mann-Kendall test. What is the test like it will tell after giving the input values, whatever the values you are getting, right, any extreme indices value for a period, you input that one, then automatically it will give the whether it is a positive increasing trend or decreasing trend or neutral, there is no trend. So those things you will get. That's very easy. You can see for formulas you can check. So any of you can check, lot of you can see information, you can easily get these equations. They are standard for the analyzing this. Any of the data, not only these indices, any we want to statistical analysis about the trend in the data, you will check these things. Okay. So you can no need of worrying about somebody's like a formula, you can write your own code, especially for these indices, right? No need to depend on somebody's programs or somebody's software. You can write very easily, you can write in the even Excel formula you can write in the any of these things, R programming or Python you can write your data sets. So only data set you get and then you can write your own formula or you copy code and check for your own work. Okay. So here these things actually the asset, right, there are way of checking like a trend. We want to see this extremes analysis, either the seasonal trend or annual trend. So you can make for this thing, this is like a different trend these things, and it is like 95% or higher most of the times. So here these are all like a how you can work in the with the, you can see once you are getting the values. So means 4 different type of test, means like a each Mann-Kendall test there are modified some people, then they give second test like that. So those things all we can check in all these you can see we give the references, our references and then other important papers, you can check there more details about this test. So change point, one thing I said, right, in the whole data set normally one is like we are more interested about trend, second is like a change point analysis. Why this change point analysis is important? So if you keep all those, you can say one of the indices on a you can say number of times which is coming on axis and on y axis like this value, you can see suddenly there is a graph is moving a trend, suddenly there is a sharp rise or sharp fall is there. So it will tell it will says that there is some change point is there, means over a time. So after some time something like some climate existing there, over a time that particular climate is changing. For example, you take the Hanmakonda, this region only, maybe some particular monsoon season is arriving in some particular months. You can say last 50 years for example. So last 20 years that may be changed, right, the possibility, right. So that all things you can get from this calculation of indices. You can see all those indices, you will get really where that change point is there. That is also very important in this analysis of the data set. So once you put for one gauge point, right, you can get all these information, 1 point, 1 grid point, all these once you are getting the indices, to draw graph means most of the things you can able to get. These are some of the, you can say just like a, once you are getting trend, right, so you see here there is a downward you can say the showing the arrow, right, something downward the thing, and something like a just like a point and something like a upward. So here wherever there is a upward is there means increasing trend, downward means like there is a decreasing trend of the particular indices or parameter. Okay, nothing means like only dot is there is a neutral you can say trend. So there is like a one time first, for example in one test it is maybe like a, here what we did is like a anything which is showing the 3 tests or modified test 1 like that, right, any passing in 3 tests means 3 tests is coming negative means it is taken as a, yes, it is like a decreasing trend is there in the particular parameter, particular grid point. Then all those things, right, you can see on the background you see these grid points, and background you are seeing the some you can say color variation, right, that's interpolation. So very simple right now for us actually we are getting a grid point wise, right, any data indices. We can very simple thing you can do after grid point you are getting any indices, we can do spatial interpolation, any interpolation technique you can apply. So that technique then you can get a how it is spatially varying. So that is more important. You see here for example you are getting at some increasing or decreasing trend, but this trend value will be there, right, that is called Z statistic. Okay. So that value will give also like a trend increasing or decreasing, how much intensity, that is also important, right, so that you can go get by this interpolation maps. Okay. So it is like a in our case, like we did for this long term trend, this thing actually, this we are saying that trend from the almost like you see, almost like a near to the, you can say the 100 years, the data whatever is available in IMD, that data set. So it is like a pre-monsoon, you can say the monsoon and then annual scale. So this is the three scales this particular thing is studied, and what we observed is like a increasing trend. Trend means increasing trend means what? All those you can say the you see CDD, all the indices we are seeing, right? Especially this rainfall trend, it is not the indices. So this is like a normal value, not indices. This is the increasing decreasing trend. Now we can see the indices, you can check actually that like annual rainfall, these things. So these are all like a simple values, but later I will show you like how we will see the, you can say the trend in the indices, like a number of rainy days increasing or decreasing, number of consecutive dry days, wet days, so 95% rainfall. So those things also same way we can make. So this is like you see the next, I think you can see on those things. This is extreme, this is the, you can say we are more interested in this particular study. So here so this is like a extremes. So there is a rainfall increasing or decreasing, that is one aspect, right? But we are sometimes more interested in how the extremes are changing. For example, 95% rainfall, whether it is increasing or decreasing over the years. Yes or no? So that thing we will see here. So this is like a some of the. So you see, this is this particular basin whatever we studied. Like you see that there is no trend in the number of consecutive dry days or 5-day rainfall, like a RX 5-day. So similarly, there is increasing trend in the total precipitation. So this is like a, on this you see. So this will give a lot of information for you, like increasing trend in this 95% total means what? Means extremes are increasing. That's where we can see in that basins more times like there is a chance of getting flood. So that one indices, like if you get all this information, right? You see, for example, 1 day rainfall is increasing means what? Number of times that is coming means what? There is a more chance of occurring floods, right? 1 day rainfall is more means normal, that is like a create to more number of times the flood. So this all information we can get in the here. So here this is like this is also, you see here the very important thing, like some of the why we have to go for specialists for this purpose. So one grid point you know, but that will not solve your problem. Means most of the times you are studying for a basin, state, or you can say one country, right? So there we need to see a overall spatial scale, these things you have to see. So for that, so we can see the, for example, if you do this type of, we can say spatial scale, we can say like this. You see, increasing trend in this both, you can say number of wet days and dry days, upper portion. That is also one information, right? Important information, right? Upper basin, how it is behaving, on lower portion. So the reason, like for example, why this particular basins I told, right? This thing, if you see the of course dam, those things we didn't kept in this particular study. So if you go for these regions, for both these, they are like a very coastal plain actually, plain region, more easy to cyclonic effects, and all the cyclonic rainfall will come here most of the times. But you go for here, there is a lot of hilly regions, you can't get much effect of those things. It will become, most of the things will occur here and later it will become slow down. Normal cyclonic or other events. So that type of all things we can get by looking at this spatial type of information. Similarly, some of these things. So similarly, the wet days, so increasing trends, that will give us like a information of how number of wet days increasing means like a number of amount of rainfall, where the 1 mm more than that is like a number of days are there. That also will give us more amount of rainfall is maybe available in the future. Okay, but it can either create a, you can say floods definitely, but sometimes it is useful information that water is also available more. Okay, so like that you can study. This is some of the important things. This is all like a table, like it's like all like a extensive you can study, like to see like each and every aspect, annual, winter, pre-monsoon, like how these particular, you see there are so many grid points, right? In that grid points, like each and every grid point, like how many times the test is like a confidence, like there is an increasing trend, decreasing trend, neutral, right? All those things are studying, like accordingly it will take out of, for example, 13 events or something like this is there, like 13 or 19 grid points. So all these grid points, how many times this particular thing is like a either positive, increasing, this is like a positive or increasing or decreasing trend. So it's like a understanding the number of, we can say, times. For example, so out of this, for example, rainfall, you take the things. So here how many number of times it is like a test is like a giving the, you can say, the increasing on the out of the things. So this will give the information of, so here the increasing by decreasing, you see the plus negative means like a number of times increasing and number of times decreasing. So that will give you idea, like for example this case you see 33/9 means what, in the, you can say, Vamsadhara basin 33 times we can see the increasing trend. 9 means it's like a more or less like a side like increasing trend, it's like that type of information. So this is like a give the information of what exactly those things, this is like a just thing. So here we can make the magnitude also, like once you are that magnitude also, like just now I only increasing or decreasing, right? Sometimes you are more interested in what going to be the value. So this is like a magnitude, we can make that one like a once that z static like we can calculate that magnitude also, it will give you also information like how much. So even though it looks like a small value, but it is, you see for a decade like that value increase means it will like a important actually. So those things are all like a give the information, like you can all do this type of, you can say, calculation. And after you are getting trends, right, you are getting this type of values, right, then finally the main thing is what going to be the background, like you are I think Sridhar is going to explain like all the drivers of those climate change, or what going to be the important factors which are going to, like we are getting indices, right, but we are to, and at the end we need to check what are the reasons for these indices, like why this number of consecutive dry days are increasing in a particular basin, why number of 90% rainfall are increasing. So for that we need to have some background driver, you can, this is called check actually. So we need to see what may be the things. So like we are seeing the sometimes like a data set also some of the issues, that's what is the one of the thing you are identified like inhomogeneities. So one of the thing is like if you see first website I showed, right, one thing. So they mention like one of the thing you need to test is called, so data we need to make a test that is called homogeneity test, means like a data, the data is like a not like a, so it is not following the particular pattern, it is like a lot of, you can say, irregular values are there, then you think that there is something problem with the data itself. So most of this, for example IMD data they are giving, right, what are those data set, IMD grid point data set, whether it is observed data we are saying, but what type of data it is, whether it is station measured at that point, grid point, it's a reanalysis, it is interpolated data. So they are measuring at some grid points and using, applying some interpolation technique and they are generating. There is a chance of error or not? So sometimes there is sparse gauge stations are there, you are interpolating. Your value definitely will go not, you can see it will not come correctly. So that's where the question of that inhomogeneity, those things are come into picture, that we need to check. So just we are getting values means that is not the case, you need to check this test. All the process of testing, how things are, so it is well documented. You can see some of you whenever you are really making the studies means you have to check those things actually. So we also like checked the water data like near gauge station that thing, and we are given in the paper also like what are things, like what type of, how we check like on particular data whether it is really correct or not, like that. Okay. So here this is the some of the things which are like a, this is the, this particular these two basins, this is like a, whatever the tropical depressions which are becoming like a more, they are increasing more means definitely we can get all those indices, we will get more, right. So these two basins are very prone, very nearby, just they are very nearby and they are independent basins. So that will like easily we can expect these things, this type of, we can say, the trends, increasing trends, especially for the rainfall and other parameters. So these are also like a, some of the things like a, away from this thing like a local convective process or topography of the region also, maybe like a, how the monsoon is setting every year, like so like a, even though we say like a monsoon is setting, so the how the winds are coming, the direction, those things are all very important, right. So those things also over a time period they will also matter, like how much is particular area is going to get a rainfall. Okay. So those all things you can get in this particular thing. This is all like a summary, these things, and this will give a lot of idea like from starting like a taking indices and finally analyzing the background thing. This is all like a we did the all these things, and then it is like a, these are all like a, most of the, you can say, observations. These are all like I am saying like a, these are the, because of more number of indices, most of the times all the indices related to rainfall are coming more means there is a more vulnerable to floods. So that's where we need to see that we need to go for a either like a hydrologic regimes or flow studies, and then accordingly how that extra water is, the main identification is extra water is there. Then there is a possibility to construct dams or to manage that, you can say, water. All things will come into next stage. Okay. So this is the one study. This is like a more information like that you can have a look at these things, and this anyway all these things are shared to you like a drive. I think today we are going to share to all of you. You can see more detailed information which is explained here. You can check those things later on. Do you have any doubts also you can ask. So this is like a one basin we are studying, right? And similarly there is one special case we will see here. This is normally this particular region like a maybe some of the place where you are coming also this type of things may be there. So this region is like a very important or famous for the tank systems. Okay. So tank system means like a ponds, or you can say big ponds, or like a lakes you can say, but they are not natural, they are the like a human constructed those things. They constructed not like a now or long back actually by the ruled over the ruled this particular area, the dynasties, they constructed all the things. They are called, why they are called cascade means they are all connected tanks. So this region, for example, this Warangal region, right? This is in the upper, you can say the, so like if we move, so like near to the Godavari river, for example, this is like a very close by, but it is like a, we are in the ridge portion. We go down, then only it will come. It is the, all the river is in the valley region. Then how this region will get the water? Where the water will come? So what they did is all the streams, wherever there is a sufficient place is there, since it is like a terrain with like a little variations, undulated terrain, right? They can easily construct the tank systems. So accordingly they made a chain tanks. So these chain tanks are like a very important for this region, means the storage of water in those chain tanks and usage from the agriculture and conserving those things are very important actually. Okay. So this Warangal and especially for this Telangana region and some of these Karnataka some parts, Tamil Nadu, you can see this type of tank cascade systems. So what we also made a one study for the extreme indices for this one of the, you can say the basin in this Telangana region. You can see this is the thing. So this particular basin is called Maneri basin. I think some of you may be aware of this thing or that region. This is like a, this particular in so many big reservoirs are there, like a moderate size reservoirs, and the same time so many tanks. You see the, you can see here also like a few things which are shown, but most of the times the so many this thing, so many tanks are there. We took a one small region, so that region, and you see the tanks. These are the what I am saying is called cascade tank system. Okay. So like we made a study, like I said, like we are like at the part of Spark and further with all the scholars, it's like Sridhar, and we are all studied this thing like how this particular system, whether water is going to available in the future or tanks we need to be regenerate. So these all things are we studied, and then for the initial work is like how these indices are varying. So the thing I will show you here, few things. So we took the few important, you can say things like parameters for this particular thing. So this is the, I am saying about statistical test, that's already I showed, I told you. So these are the way you can see this particular basin, same, you see the trend increasing and you can see the trend, and you can see most of the times you see this is the decreasing trend in some particular thing, monsoon, and then these are the things. This will give a complete picture of how the precipitation temperature is going to change in this particular basin. So within turn we can tell about this is like a same, like all those you can see the indices, extreme indices, all those things. So you can see the tick or these colors, all this will tell you that really there is something like a, for example, this type of color, they will tell you like a something is problem there. So we can focus on those chain tank systems, and further you take those values and from there you will analyze whether the water is going to come more or other things we can check. Okay. These are the some of the, you can say things we observed actually the thing. So this we see that there is some shifting precipitation patterns in this particular in this region, so that chain tank system is to be given more priority to preserve those things. Okay. So here same thing like we made a like a, we are getting data right, so that easily we can present to the some, you can say the dashboard, so that people can easily understand those things, that case thing. So quickly I will show you within 1 or 2 minutes. This is like a same thing calculation, but we will see as a dashboard. 1 or 2 minutes I will conclude this one. So this we did for Anamakonda region, this thing. So this is some of these things we are trying today. So this is the, just you see the thing, one grid point, like we are just showing the some of the values, right? So here this is like a, you see some of these I am saying about, right, each year, and then this is the way the indices will be there. This is the way you are doing today, you are trying, like you will check number of things. So this is the way the each and every, this is for one grid point, like a different parameters. Some you can say maybe some 10-15 parameters we can see. So these things we are bringing in the, you can say this, this is the each grid point, like you can make the, you can say the trend, later calculation of a trend, that calculation you can make, like so many values will be there, that in that we can make this Mann-Condell test and you can see one grid point, one value. So like a background calculation. So we did interpolation and you see this one like this we can make. These are the way you can make this thing, right? So this is okay, you are normally you are doing previously, but this is whatever I show you, it will give you one idea for you. So these are all things, right? This is what I am saying, this is different. So means what we can do is, whatever you do all the things, right? This is easy for, like we can easily take to public domain now. Now is possible that one, so you can bring into the simple WebGIS thing. I think most of your geospatial background, or you can some of the having a background studied this thing JS, you can make all the things into available in public domain, all these indices. So whatever you calculate, right? So you can put them on into the indices, and then anybody click on this. What we did is, like after interpolation of the, you get bigger grid point, right? We will get a spatial, right? Then once again made as a each grid raster. So means each and every grid point also will get the indices. So for example, you click on this campus one grid point, you click means you will get the indices. That's what is the way done. So this is the, just you can see the parameters indices. This is the indices actually. You click on the one point, you can get all those. You see one parameter, like one point where click right here, for example, you will get. So this is the way we are making. This is the what I am saying. It's done. So here climate, you saw like fundamental 27 are set, like they are there. You take whatever things required for your study, and accordingly you can analyze. You can take to the level whether you are studying for your purpose, and then you can take and you can make, or you want to make it public available, you can make into the WebGIS platform also. So from starting to end, whatever we discuss, right, almost you will try those things in the lab, everything. So you see how you can get that. That's why we are explaining all things, how the things are done, and then same thing you will experience also how you can also do these things. Okay. So this is the, I said like a like Sridhar, and we are all like these things, we are doing all the things. Last, these are all like a, they are available in public domain. You can all check these papers, and then all these things are whatever explained, everything, most of the things are available here. So these are all the important papers, especially I am saying about the definitions and then how that indices are derived, all the things you can get. This especially, this paper is important, you can check. Yeah, that is the, I am done with my side actually. So you can now open for discussion. So you have any questions to ask about this, all these indices, how those things we can apply for a particular case study, and how we can get the results from those things, and how we can use for some. Any questions? Yes. Yeah. How? Yeah. So there is like a, this question, I think one, I think we are going to explain, I think next tomorrow sometime class it is coming, and Sridhar is explaining some of the things. So and machine learning also, like the next, I think next week you are working on those things, some of those things. So one is like to get the future data, there are different ways are there. One is like I said, like a regional climate models or global climate models. They will give historic data set, right? These are all. So with these things, so getting all those trends, right, they can project for the future by using the regional climate models or global climate models. You will get, that is one way of getting data set. So like for example 100 years, right, next 100 years they have forecast. So some of those results we did also for same basis, we will show in the next tomorrow, day after tomorrow class. And other way of doing things, like exactly what you are saying is, for example, this all 100 years data is there, right, daily data set. So you can easily now with the present, you can say AI and machine learning algorithms, you can easily do for one more year. For example, this June month rainfall is there, right? 100 years you give the input. Next June month, for example, next year, for 2025, right now we are there, right? So this you can here predict, actually you can predict. For example, this month we are there right now in the August, right? We are getting to going to get August, right? So you can predict the August rainfall. So like next 30 days you can predict based on the last 100 years of the August rainfall. So the question is like what you are asking, like how much it is reliable. You see that that is like it will at least give some trend. Like for example, next August, normally first 5 days are heavy rainfall, later it will be reduced, later it will come, like that it will give one trend and values also. But so those things actually will give accuracy maybe up to, we assume, 60% or 70%. Why they will change actually? Climate is not like a, it's not parameter like some other, like a, some for example like a health, there you can health systems or some other systems, they are very clear, right? Machine learning we can easily apply it, since how it is going to change we can make. But climate is highly is very variable, right? You can't able to bring into the machine learning to the highest accurate level. But definitely for that, what is the way out? So what you can do is, there is something called global, you can see that actually this study only, there is something else is there actually that we didn't give. There is something called NFS. There is a forecast data will be there. So you are forecasting by your last data, right? There is something called like a, based on the climate, all variables. So there is a national forecasting is there. Our India they will make on national level, actually the NASA, those people also forecasting for next 1 week. You take those data sets, you take your things, that is called error correction. You can try to correct the data set, and accordingly you can make one more data set. That is like a more close to the observed. Then you are getting, for example, last 10 days rainfall, you know, right? And next 10 days your machine learning algorithm is there, right? And you have the forecast data also there, right? So by using all these three also, you can once again apply machine learning technique. Then you can get a more corrected data. Okay, this is like a different ways of techniques to get the closest, you can say, corrected climate data. Okay, that is like one of the important area what you are mentioning, that predicting the machine learning algorithm, correcting one of the area, and some of those things we are addressing in the coming days actually. Hmm. Like a 100 years of the flood, all those things. Yeah, to return period this thing. Definitely we can do, but most of the times like a flood is like a rainfall converting into flood. So it involves in between a lot of hydrological process are there, right? It land is land cover, digital elevation model, those things. Some area may be going to heavy rain, but it going to absorb, and then we can't get that as a rain. It can't coming as a you can say the runoff flood. So definitely the 95 percentile those things they are useful for analyzing those only. But 95 percentile they are repeating like what you said, like a heavy rain, and how many times that repeating, like a 95 percentile of those extreme events, precipitation events, they will give an idea of that area is going to flood or not. But those things you need to substantiate with the flood also. Flood like a, we have the gauge station data is there, right? Outlet, those things we need to substantiate. Both things combined we can see how many that will like a combined you see, like how many times that rainfall extremes are there, how many they are converting into flood. See, only rainfall you are saying. Only rainfall means I said like you can do with indices of the rainfall indices are there, right? With that you can make that what that is only will give you some information only, like a 70% information only regarding flood. Every extreme rainfall event may not be become flood. Okay. For example, there is an event going to occur in a summer, some rainfall event, one day, very heavy rainfall. That may not be counted into flood because of previously we have a lot of dry days are there. Same thing is occurring this August month, that going to be become flood. Since already it is like a soil moisture, all the things is there saturated, and then it is like a not take water much the basin, everything going to flood. That these are all like a so many things we need to see together. Yeah. Yes, yes, that's where it will give you a that signal, climate change signal, or what are the different like a drought signal. I think some of you are also studying, I think, drought related things. It will give drought signal. Also, I can say whatever extreme rainfall signals. Those all things we can get in that indices. Shift is there. All the things also we will get. Everything we will get through indices. That indices are important. That's why we are doing the not only per grid point wise, based on all the grid points, and then do interpolation. Then you can see, you can get all those information. You will get. Is that okay? So more things like we can discuss in a whenever we are getting any off time. So now I will stop at this point, and I will hand out to Sridhar to proceed. or we will take a yes, yes, 5 minutes break we will take, then once again we will come back and then proceed. So later we can take the in between the class, you will give the break for the whatever the break for means that snacks, those things will come, we will take a break in between.
First lecture from Dr. Venkat Reddy on indices which are really very closely tied to where we are heading today's, in today's discussion. But since yesterday was the inaugural day, we had some, things to catch up. Whatever is left out yesterday, I'm going to start with that. But we don't need to go into the details about all these SDGs, but I just want to introduce the terms and then from global scale to India scale, how these extreme indices are looked at for a given year. I'm going to actually refer to the published report that you will then be able to connect with this morning lecture, and then we will then start with the basics about hydrology to bring everybody up to speed on water cycle, water budget, energy budget. That's the plan for today. And if time permits, I will also talk about land atmospheric interactions and what goes behind these extreme events. Dr. Venkat Reddy alluded to that, suggesting that there are physical processes that are involved in this extreme events, development of extreme events, and how that is changing, especially with monsoon because of climate change. That's the, kind of a wrapper or a kind of a closing conversation that we can have on this topic for today. So it's about 1 hour and 50 minutes that we can have, but we will have a break maybe roughly in the middle of this 150 minutes, 1 hour and 50 minutes lecture. Before I start this discussion, I wanted to ask you, are there any questions from the discussion that we had yesterday? I know, it's pretty basic stuff that I talked about yesterday. Was that, I mean, is there anything that comes to your mind that you want to open up the floor for discussion? Anything that you want to clarify from yesterday's discussion? Not much, right? That's okay. You know, is my microphone working in the last row? Can you all hear okay? Okay, good, good. Okay. I have the names of you, all of you. So I would like to interact with you. It's not that I would put you on the spot by calling your name, but during the break or even when you ask some questions, tailoring to your research background or what you are really wanting to know, that will help me to understand when you are answering or asking the questions. But I will also get to know you more in person, right? So that's the objective of this whole session, interactions. Coming to the Sustainable Development Goals, this is the goal set up in 2015 for 15 years. Up to 2030. United Nations actually came up with this plan in 2015 in Paris. We talked about Paris Accord yesterday, where they wanted to cap the increase, the change in temperature increase to be capped at 1.5 degrees Celsius, if you all remember that number, right? The reason for doing that is to make sure that the planet is not going out of control when it comes to all the the inhabitants or the species or the natural systems that we have are intact. Even 1.5 threshold is kind of a modest goal, but I don't think we are anywhere close to reaching, except India. I think India is really close to achieving that target, that not many countries are able to do that. But the purpose of doing that is to look at their influence on all of these 17 metrics that they are coming up with. It's basically, let's say, if I have to zoom this in, no poverty is number 1, zero hunger. This is for the global scale, for the good of the global population. They are setting this agenda. Number 3 is good health and well-being, quality education. So likewise, you have now when it comes to this particular class, There are a lot of, not all of them are connected directly to us. It's a broad area of SDG, sustainable development goals, but we have a few of them that are very close to our interest. For example, clean water and sanitation is number one for us, directly connected. Sustainable cities and communities. When we are talking about extreme events, floods or droughts, particularly in cities, they are going to affect. So number 11, and then climate action, number 13. How do they plan for mitigation? Yesterday we talked about mitigation and adaptation, right? So number 13, life below water, that's marine life, but we are talking about sea surface temperature, how that is changing. There is some connection to monsoon, how that will bring rainfall into the land. So there is some kind of connection. Life on land, right? That's another connection that we have. So at least, and then public health, no hunger, no poverty, these are also connected. No hunger means, how do you connect hunger to what we are talking about here? Is food security. How does food security come into play for civil engineers or geoscientists or water people? We are talking about irrigation, water for agriculture, availability of plenty of water for growing crops. That is connected to producing enough food for people, so then there is no hunger, right? So you can actually connect. So the idea here is to then show for each of these 10 metrics yesterday we talked about. If you remember, the planet health check, what people try to do is to come up with what is the level of atmospheric carbon dioxide, right? That is number one, emissions, that we talked about, that is increasing, right? So with this, what we call hockey stick, basically it is gradually increasing. If you just look at this plot, this ppm of CO2 in the atmosphere from 1960, Hawaii Mauna Loa site is the first place they started measuring, and now after 70 plus years, it is up to 417. Now they are relating that to all of these SDG numbers like 13, 14, 2 and 3. These are directly connected to increased atmosphere. Enhanced greenhouse will affect ocean, will also affect climate, will affect food production, will affect air quality. That means the city quality of, or number 3, that will also be affected, which is basically good health and well-being, which we are witnessing. For example, in Delhi, if air quality is bad, people are asked to stay home or work from home or closing the schools and those kinds of things, right? So you have connection to carbon dioxide in the atmosphere. In that case, it's the smog in our place is basically because of agricultural residual burning from Punjab and Haryana that causes. That's the study that they are coming up with. But again, there could be many number of reasons. But what I'm trying to say is, for every metric that we talked about, people are now able to see the connection. For example, the CO2 increase is very close to your temperature increase plot. This is called a hockey stick. When somebody refers to you as hockey stick, you should remember, it's a stick that used for hockey, right? Hockey game. It's the same kind of a curve that they are talking about, hockey stick graph. And then temperature, for example, from 1860, we have very limited data that we are talking about here, right? 1960 or 1880 in this case, 1860 to all the way up to 2025. Not much, right? 165, 66 years, which is absolutely, not sufficient to fully understand. There was a question about, how do you know? We'll come back to that discussion later again, the return period calculations and what is the, if you have only 50 years of data, how do you calculate 100-year floods or 500-year floods or 1000-year floods? People calculate all that, but it's a stochastic exercise that we will talk later. But the idea here with 150-year data, 150 plus year data, we are still looking at temperature increase, historic record of 1000-year floods. 1000-year floods you cannot calculate with 100-year floods. 100-year data. No, that is not the case. You can. It's a probabilistic approach. P is equal to 1 over T. That is the the calculation for return period. and of course you put the return period whatever way you want, and what is the probability that you get out of that is the way you calculate. But here, coming back to this discussion, this hockey stick you can see from all the models from historic times. We have kind of confirmed with observed data. So we have confidence in these numbers. All the models are showing, I mean all the observed data and the models that are showing here are pretty comparable, right? Very close. Then for the remaining time for the future that we don't have the record, I'm sorry, this is also historic anyway, but for the remaining time after this historic times, we have to rely on these models, assuming that they have predicted well for the past, they might do well for the future. That is the idea behind climate model justification or verification. Coming to the next one, global mean surface temperature, that's also increasing. That's another metric that we talked about. If you remember the graph or the schematic that I showed, the second metric that we are saying is when you are talking about the health check of the planet, after CO2 increase, temperature increase was something we talked about. See here how many of these SDGs are directly connected to increased temperature. These are the processes, whether it's atmospheric process or land surface process or the physical quantity that we are talking about. In this case, increased temperature will create more evaporation. More evaporation means more water that will be lost. So there is going to be a drought issue or water security issue. That is one box that I am talking about. Likewise, for every box that we have here, there is a physical connection to planet Earth, and how that is actually used for making policy decisions. How is it going to affect the goals that we want to achieve by 2030? We got 4 years left to achieve the goals. We have never come close to controlling the emission or controlling the increase in temperature. So you can clearly see these goals are not going to be achieved, right? That is the overall message that you want to be looking at here. Then again, greenhouse gas, I'm sorry, this is ocean heat content, that what we are talking about. Ocean, we'll talk a little bit more about it later, but oceans store a lot of heat, right? And they accumulate their capacity, thermal heat capacity, holding capacity is really large compared to the atmosphere. But when they are showing some changes, that means we are talking about aggravating the conditions really fast. And when ocean heat content is increasing relatively, anywhere from the surface up to 2 kilometers below, they are talking about in the ocean. And all the changes that's happening, whether it's because of acidification or increased sea surface temperature, or all this mixing that's happening, causing biodiversity issues, fish kills, or the density difference that's creating the ocean currents to move back and forth, that will slow down the monsoon systems. They're all connected. So these SDGs, there are at least 7 of them that we are seeing here are connected to ocean heat content. And ocean heat is increasing. Sea level rise is very clear, that we have seen so far. Many coastal cities are vulnerable, and because of coastal cities and many of this infrastructure that are going to be impacted, you have more number of SDGs that are directly connected to sea level rise. Likewise, we have ocean acidification that is connected to many SDGs here. I am quickly going through, but you have these reports that will be made available for you to read for your information. You are not directly going to recreate them, but at least when you are connecting your motivation for research or justification for why climate change should be considered in your kind of analysis, you should be having some reference like this. Glacial mass balance, basically we are talking about ice caps both in Antarctic and Arctic, and also higher elevations, where we have glaciers, whether it is high latitude regions or Himalayas, you have all these glaciers that are being melted away, and that's causing a big problem for many things, right? For example, Ganges that starts in the Himalayas, because of the snow melt or the glacier, we are going to have more of those things melting faster, and that means maybe by 2100, if there is no glacier, we have to rely this perennial river. We call it perennial because in the monsoon season it gets runoff because of precipitation. In the non-monsoon season, still you see the river flowing because of the snow melt, right? That is constantly happening. So we are not going to have that perennial systems anymore that are dependent on these glaciers. So that is an example of how they can be connected. So now you have all these SDGs that are directly connected to glacial mass balance. Arctic sea ice, that's not directly related to us, like I said yesterday, that is also decreasing. The millions of kilometers, square kilometers of sea level, sea ice content is decreasing, melting. It's what is it going to do with us? It is going to melt into the sea, and it's going to create increased sea level, rise. That is a possibility. And then of course, when the the heat systems, I mean storage that I talked about, oceans can hold more heat, and now with sea ice, it may have the reflection more solar radiation when they come. But with ice that is gone now, you are going to see that radiation heating up the water, which will also increase the ocean heat content, or it may even create additional issues that we talked about: increased sea level rise, monsoon changes here in the tropics, sea ice extent that we talked about. And then, I mean, these are the metrics that are related to SDGs. There are other things in climate scales when we talk about. El Nino is one example. There are many of them. I don't know whether we will cover in this 10-day lecture, but if time permits, we'll do that. El Nino, MJO, La Nina, and PDOs, ENSO. These are the metrics, like climate indices, similar to extreme event analysis that you did. There are ditto, climate indices that are available. The only difference is whether extreme weather events are on a shorter time scale, these climate indices on a longer time scale. Okay. So El Nino, that is coming every 5 to 7 years. When it comes, because of how it happens, probably some of you might be familiar. This is South America here, right? This continent is South America. Peru is here. Sea surface temperature becomes abnormally high around December in that area, and oceanographers and people that study climate look at that sea surface temperature anomaly. They call anomaly. When that happens in December, they immediately start watching that more closely, because that has ramifications all around the world. For example, when that spreads across this Pacific, it becomes a problem for the rainfall patterns. There will be more rain in southern part, central part of the US, less rain on the northern part and in Canada. That's an example. India is not directly affected by El Nino most of the time, but South Asia, Southeast Asia, and South America, South Africa is affected, and central to South America is also affected. Dry conditions. Some of these places have more rainfall during El Nino years. They are able to confirm this over the number of years of record, by closely observing these patterns, monitoring sea surface temperature. There is a good level of confidence in getting these climate indices calculated by the community, scientific community. And once they are able to say that, they can even forecast for 6 months ahead of time and say what will be the precipitation, temperature conditions, or mostly precipitation they are talking about, when the El Nino scenario comes. So that is the kind of relationship that we have. This is on top of climate change. This is not climate directly connected to climate change, but there is some connection to climate variability. We are talking about the past data, and then using that to predict for the near short term conditions up to 6 months to 9 months. Now they are able to come up with a pretty good confidence on predictions of what's going to happen in some regions. It may be different for different locations within a region, but on a regional scale they are able to convey some of these things more clearly. This is the annual average temperature anomaly relative to 1991 through 2020 average. It's about what, 30 years. Normally for statistical purposes, normal distribution. You see, you saw the bell curve, we call bell curve, right, with tails having extremes. That is the normal distribution, and for drawing that kind of a distribution you need minimum 30-year data, right, that you all know for records. So they are using that 30-year record here to see what is the anomalous temperature for a given year. In this case, they are talking about a given instant annual average temperature anomaly relative to that 30-year period. From all over the world, they are seeing that you can see the warming conditions extremely high. I was just in Alaska a couple of months ago, and I could see people are really witnessing Arctic ice. I'll probably show some of these glaciers that I visited later. Yeah, go ahead. Yeah, right. Anomaly. What is anomaly? Basically, thank you for interrupting or asking that question, because it's the benefit of the class now. Let's say you have a temperature record. I'll relate to the data that we discussed previously in this class just last hour. 1 year of precipitation, right, daily data that you have, if you total them up, right, you get the total annual precipitation. Let's say for Warangal, it's about 1500 millimeter that I say, right. So likewise you can calculate for every year total precipitation, right, and then for probably the case for our conditions also for climate change, we may get more rainfall. That is a good thing for us. India might benefit, but we are also going to have more temperature increase, which may also evaporate most of it. So we don't know exactly what the feedback cycles are. We will talk about feedbacks and physical understanding of those things. But just for grasping the bigger idea here on a global scale, you know how people are coming up with a map, fancy map. This looks fantastic for me because it gives you a good picture that rainfall alone, if you look at it, is so highly variable that you cannot make a single conclusion from this, what's going to happen overall on a global scale. So you have to really look at the local scale impact. So that's where our roles come into play. These kinds of map really help us understand that part. Yeah. So now I will actually, again, some of these things are taken from these kinds of published report. I'll speed up here a bit. This is not going to be legible or readable for you. This is a global, by region they are saying, in this case, South Asia, SAS they call. And I'm sorry for really having this dense map here. If you look at this legend here, they are talking about, this increase is in pink color, blue or brown, decrease black color, right? And then 3 dots means high confidence, 1 dot means low or no confidence. If you look at South Asia, that is our country, India here in this case, hot extremes are increasing with reasonable confidence. 3 dots, high confidence. That's how you would interpret this. I will repeat this once again. This is the global map of the regions by letters, English alphabets they used. SAS is for, these are all in that figure captions that you can read later. South Asia is here with increased tendencies of hot extremes from climate change analysis that I'm talking about is a possibility for South Asia, including India, with high confidence with respect to temperature. That's how you would relate. Heavy precipitation, if you come here down, yeah, we are going to have little bit more precipitation, little bit more precipitation, that is increase, right, green color that we are talking about, and South Asia, that is including India, with 1 dot, which is not highly confident, we are not sure, but it may happen. that's where the roles of modelers come into play. At the end of this class, if you are all understanding what's happening with climate change and how would you integrate them into modeling to predict exactly, you will address that question. If you can take one such question, how much of confidence that we can have or improve to have better precipitation for a continent or subcontinent like India, that's a big research question to address. So we'll talk more about research questions and how you formulate research ideas on the last day or last but one day. That's in our class also. But you can relate questions like this. How do you pick research topic? Looking at these reports and say what's exactly happening and how are they interpreting? Why are they having no confidence or low confidence? Can we have better analysis to improve the confidence? Those kinds of things you can have. But message here is temperature is increasing, precipitation might be increasing, agricultural drought they are talking about, or ecological drought for South Asia. Here it's hashed, right? There is a slanted line here, I think, maybe not, yeah, I think it is there. That means they are there but not highly confident about what's going to happen with drought. So that means it opens up a really good question about what's going to happen to India on drought. We will talk about drought day after tomorrow, I think. Full class is on drought. So you will fully understand how to model drought, what can we understand about drought in India and all that we will say. We will discuss in detail. But on a global scale to regional scale, when you look at, people are not sure what's going to happen here. It's a wide open field for us to think about research, right? So it's a summary from that report that I'm trying to gather. One other inequality that I talked about, I don't want to kind of be a person to criticize anybody or anything here, but what generally these reports say I'm interpreting here, right? So these are countries, each one is a country, right, dots. Many countries that are here, basically the vulnerability that we are talking about on the y-axis and emissions per capita emission. For 1.4 billion people, if you average the emissions divided by 1.4 people, our emission is really trivial, insignificant, right? That means we are one of the low emitting countries, but with high vulnerability scenario. This is true for many of these middle income or low income countries, whether it is Bangladesh or India or Sri Lanka or Maldives. They may be going underwater, or Solomon Islands, Pacific Islands. There are a lot of small islands. Tuvalu, for example, they are talking about not going to exist. They are all coming here. So the simple interpretation is that vulnerability is high for really lot of countries that don't even produce any emissions. Maybe rich countries, Europe or Asia, North America like US or other countries are here, high emission with less vulnerability. Per capita consumption and the emissions of all these fossil fuel related GHGs are higher for some of these advanced countries, but they are also not going to be as vulnerable as some of the other countries. That's the interpretation of this graph. Whatever it's worth, you take it. Don't go into the other aspects of it in terms of policies or excuse me, policies or politics or whatnot. As a scientist, when you look at how can we change this map, what can we contribute to improve the well-being of the planet or the people, or to improve the conditions, that's probably a lifetime goal for each of us. It can be 50 years of career that we are talking about here. So, oh, that's a big question. That's the discussion they had in the COP, community of practitioners by United Nations climate change conference people last year. It did not go well. They call it damage, loss and damage. That is a compensation. That's what we are talking about. They want to put it like in Paris Accord. They want to come up with an accord saying that these countries that are vulnerable should be compensated, right? So they even created a fund called a climate fund and they said rich countries should put money into that pot of billions of dollars, $100 billion or something they put already, um, but not many countries are contribute, developed countries, and it's a kind of an insurance thing, liability part, legal thing. They don't want to commit, so it did not go. US walked away, Europe probably did not commit too much, or many other countries did not show interest. So, but many other countries wanted to even have that verbiage of saying uh, these vulnerable countries are eligible for loss and damage or something, that kind of a language they wanted to insert. But if you become one of these top-notch policymakers and ambassadors of this country to represent UN, you will come to realize that how much of a difficulty it is to even put one word or one sentence that you think represents your country, because there will be a lot of push and pulls coming in the way. I don't know the latest situation of that particular loss and damage acceptance, but there is another meeting, United Nations Climate Change Conference, COP 30, number 30. There are 30 meetings that have happened in the last so many years. This year it's going to be in Brazil. Belém is the town name, Belém, Brazil. I may not be going, but I have contributed the report for that conference. I was in Paris just before coming to this one, where we talked about how Congo Basin is going to be impacted. So we are trying to really present that report. It's not connected directly to this class, but what I'm trying to say is these kinds of reports are going to be presented and discussed and debated and released for public consumption. So we don't know where the direction will be for that particular question. Since you asked about loss and damage, I just wanted to give a broader picture about that. Yeah. Resilient infrastructure, yes, definitely. It is part of adaptation strategy. So we will talk more about that. Certainly, it is coming. I will talk about that in day 6 or 7. I'm having all that discussion. So quickly covering again. I think I'm sorry again. I'm going slow. When questions are asked, I feel like answering in detail. So that's where I think I'm going slow. But I hope it's not boring for you. Please let me know if it's going slow. We can speed it up. Human systems, natural systems is the general description. When we talk about agricultural lands, it's a human system. We are modifying the landscape, irrigating the land. That's the connection that we are talking about. Ecosystems are forests that are undisturbed, pristine watersheds, and those kinds of other systems that we are, ocean species, marine species, and all that. So they classified human systems, water availability, health and well-being, cities, and then looking at for each continent which ones are vulnerable. And for example, if you look at, I'm just giving one example, but you can interpret yourself later on. Physical water availability for Asia, we are going to have adverse impacts, and there is also going to be a positive impact. So that's where we are harnessing the benefit of excessive rainfall. How I would interpret, for example, in this case, we may have more rainfall, let's say 5 or 10% more on a subcontinental scale for India. That means it's a huge source of water for us. You don't need to suffer with the drought conditions, provided we have good water management plans. If we have it, that's what the linkage is here. It's going to be adverse with excessive rainfall. You'll have more rainfall, more floods possibility. We saw from previous discussion, Nagavalli, Vamsadhara basins, we are studying that more intense rainfalls and flooding potential will be there. But if we have best water management strategies, minimize flooding by building structures, resilient infrastructure, we save that water, cascade of tanks in another study that Dr. Venkat Reddy was showing, increase the capacity of those structures, store more water, it supplies more water, it recharges groundwater, those kinds of things. You can make the negative into positive conditions based on how, as engineers, we come up with design plans, right? That's the connection. So I'm just taking one bullet to explain this, right? So one particular row in this table. So likewise, when you have time, read each one of these variables and see where we stand, how as scientists and engineers we can come up with a plan for changing the worst condition into a best condition. Okay, I will go on with the next slide here. Yeah, this is again per capita emissions. I don't need to dwell too much into this. Global carbon emission budget that they are saying here, global scale. India is at the very low level here in this case. South Asia is the least producing GHG emissions, as you can see on the right side, and our contribution of CO2 or methane or nitrous on a global average, when you talk about the budget, is less than 9% on the total of 59 giga tons of carbon dioxide equivalent that they are talking about. India or South Asia is roughly about 8 to 9% here. So the idea here is to get that, it is not that we should be polluting more. Okay, I am not justifying that we are okay to release more CO2 or GHGs. Don't take it like that. Even with this, if we have a sustainable, if you want to have a sustainable growth, there is a lot of innovation or novelty that you can bring in to sustain good quality life, to improve the planet's health, to minimize the mitigation, or improve the adaptation, those kinds of things that I am talking about. So change the opportunity into something that can really make this place better. That's the idea here. Okay, the last one on this global scale thing I will show here. If you see here, we are more vulnerable. Asia, with increased population because of sea level rise, Asia as such will have 64 million people directly on the line of fire because of sea level rise, compared to 3 lakh people in North America, for example, roughly 0.34 million, 3.4 lakh here in this case. So 3 lakh versus 6 crore people in Asia that will be impacted. You can see the number of people that are impacted with one variable of climate change, which is sea level rise that I am talking about. Why? In India, we have big cities, whether it is Kolkata to all the way, where you come on the east coast, to Chennai, to Kochi on the west coast, to Mumbai, all of those big cities, you have millions of people that will be directly affected because of sea level rise. So likewise, you have on a global scale, if you look at, there are a lot of places, that big cities are all, if you look at top 20 cities, mostly they are all on the coast. There are more than 20 million people, if you see. They are all vulnerable. So that is the idea. And then this feedback, I will come back again. This is an interesting graph that I wanted to study or show you. This opens up a lot of questions for us, research questions for us, which we can address later. For example, I will talk in depth this one, bear with me, because it's an important exercise for us to understand the connection. Extreme heat, right? Temperature increase that you calculate based on the today's afternoon session, let's say, extreme heat index. What is that? CDD, cumulative dry days, or temperature of 95 percentile exceedance of, let's say, threshold of 35 C or 40 C. You can come up with those extreme values, right, easily now. I mean, after today, let's say. You connect that to this particular map, which is what is happening with extreme heat. It will, deplete soil moisture. It will evaporate. I mean, good rain that we got 2-3 days ago, but they are going to be lost if temperature is higher, right? All these trees are really talking on a daily basis between the atmosphere and the soil. They are sucking all the moisture. They are releasing this moisture into the atmosphere, right? So that's the reason why we are losing the soil moisture. Where there is no vegetation, directly sun comes and takes that moisture, evaporation. ET, evapotranspiration from the plants, and evaporation directly from the soil combined, when there is extreme heat happens, we are going to be losing all the moisture, right? And of course, it's also uncomfortable. People's health is affected. Heat stroke comes, right? So that's the health part that you are seeing here, this particular box. So what happens when there is less moisture? The next one here, in the connection here, if you look at, I'm sorry if it's readable for you. It's all readable in the last row for you. Can you read it? Sorry. So maybe that's all I could see. I think this is a limitation of my slide here. Bear with me, but I think when you get the slides, you should be able to expand. And the report is also having this graph. So what I'm talking about is crop yield will be reduced because of dry conditions, right? Drought conditions. If there is drought, then there is going to be more inflation with food prices. That is the connection that we are talking about here, right? And that means farmer will get less income, reduced income in the household, right? And then you are talking about reduced labor capacity. People have to sit inside until the sun sets to go out and work. Labor efficiency is affected, or they cannot work comfortably, under heat stress conditions. Decreased quality of life that we are talking about. Increased malnutrition. When there is low food production, people cannot feed their own family or cannot supply, and famines that you are seeing in Africa or many other parts of the world because of crop yield loss. That's what we are talking about. Increased malnutrition because of reduced food security. So you can see the connection. Temperature increase, right? It happens. Don't just think mechanically, okay, I'm going to calculate using my skills, writing a code in Python, Jupyter, whatever, and then downloading all these fancy data sets. You have to pour your mind into looking at what is the impact of the number that you are calculating. How can you relate to any of the science questions that we have here? See here the connections that we are talking about, any number of connections that we can establish. That is an example. Yeah, you have a question? Introduce yourself to me again. Imran. Okay. Yeah. Yeah, yeah. Hmm. Oh, yeah. There is land atmospheric interactions. Yeah, yeah. Oh, Well, actually, urban heat islands. Yeah, I mean another. It relates to both land surface and also atmosphere. So the instability in the atmosphere causing thunderstorms over the same area brings heavy rainfall events. So the destabilization of atmosphere, if you bear with me, maybe I think we will have time to get to that point by today. I have some slides to talk about the physical process, what's happening with respect to heating. And if you can really wait until that time, and if I don't address, let's talk about it later. But it's coming. But there is a connection there between land and atmosphere, and that instability in the atmosphere bringing more rainfall when the dry air mass goes up, because the vacuum is being filled by cold air mass. But I'll talk more about it later. But thanks for that question. Again, in the interest of time, I'm going little bit quickly on this one and then move on. Again, this is on a broader scale, right? Global scale stuff. There are 4 things that I show here. Risk of species loss on natural ecosystems. If you look at 1 degree or 1.5 degrees, 2 degree increase, 3.4 scenarios. Yesterday we talked about RCPs in CMIP 5, SSPs in CMIP 6, right? That is basically Climate Model Intercomparison Project CMIP. Version 5 was the last one. Version 6 is currently going on. With any number of scenarios, 4 of them that we are showing here, India is really going to be having a lot of issues here with respect to species losses and heat humidity related risks. You can clearly see we are having a big range, I mean 1.5 to all the way up to 5 degrees Celsius increase. India is constantly on the darker side. It's going to be more vulnerable. That's what I am saying here with future. Maize yield, another one that they are showing, it is going to be affected with the different temperature increase, and India is showing some signs of stress here. Fisheries yield, we have a big coastline here, right? There are lots of fishermen community that rely on fish yield, and that's going to be affected in many countries, many regions, and including India that we are seeing. So these are 4 metrics that they are coming up with. This is from the latest report of climate analysis, right? So likewise, they are coming up with every year. So now I'm just introducing the idea of how you can read this report and understand what's happening to India, right? And that's where it will come into play, or wherever you end up going and working. It could be another country, another region, another continent, right? But these ideas remain intact for you to understand how people are relating climate change to any number of issues that are related to what you can pursue as a research goal or a professional goal. Okay. Now I am going to come back to some of the literature, basic things about water, why we need to consider water, and what is hydrology, climatology, hydrometeorology. I will quickly whisk through some of these things, might be relevant to your interest, and you might be familiar also already, but still for the interest of everybody's attention, I will start from this again. Water is essential for humans and for natural systems, right? We know that natural systems including biodiversity, forest loss and whatnot, and then natural systems that we talked about, oceans and fisheries, and humans, agriculture, cities, urban areas, all of them will be impacted. For that, water is essential. Only small portion of water is available as fresh water, right? 70%, I mean 3% is available as fresh water in the entire planet. The remaining either frozen or as sea water, right? Ocean. So that's not useful. So with that 3% water, we are talking about how important it is for us to carefully manage it. 70% of that water is of freshwater withdrawals from lakes, rivers and groundwater is used for irrigation. That 3% fresh water that we have, that includes surface, subsurface, of which 70% is gone for irrigation. That means we are talking about the remaining 30% that's available for consumption, for humans, for cattle, animals. So is that going to be industrial use, municipal, commercial, hydropower, all those things? So again, that is going to be a challenge for us, right? So we have certain amount of water coming from the atmosphere, precipitation. We have certain amount of demand. If they match supply and demand, no issues. It's your monthly income budget, let's assume like that. We get certain amount of salary. If our expenses are going to be within that salary amount, you are good. Your salary is less, your expenses are more, it's deficit budget, right? We are talking about building up the deficit more and more and more. If you have more salary, less expenses, you have more savings. That's not happening for many of us, including us, right? Many of us. But the same thing for happening for the planet Earth. We have less supply, more demand because of population increase, because of the needs that we have, and because of dwindling supplies also to some extent. We are talking about supply becoming not equal. So now our role is to understand where we have the supply more, where we have less supplies, where we have more demand, where we have less demand, and how often we get precipitation, what is the occurrence of it, what is the magnitude of that supply, how much we need for certain sectors. That is the kind of question that we want to ask, right? Again, going back to this historic water cycle, you are all familiar with this. I am still going to repeat. It's a very active system, right? On a daily basis, if you look at this water cycle, it is a distribution of water. It's essentially water in the form of three phases, right? Ice, liquid water and water vapor, or these three things are either staying in one place or moving around across this whole globe, on different time scales and different processes, for different processes. Water comes from the sun, evaporates and goes as clouds, and then comes precipitation again. Water comes as precipitation, runs on the ground as runoff, and then gets into the groundwater, and then part of it is ending up in the ocean, part of it is ending up in the groundwater system. So how do you quantify this is a question that we are asking. It is changing on a global scale. It is changing at your watershed scale. It is changing from one year to the next year. It is also changing because of the changes we bring to the system, meaning we cut down the forest, we build a lot of lands, we remove the lakes, we don't harvest the water. So we have lots of modifications to this water cycle, right? And that's actually causing a problem. And I think I'll come back to that also later. There is a slide that shows this water cycle is not valid anymore. The water cycle that we have seen from our school days is gone. It is now needed to be adjusted for all these anthropogenic, meaning human induced changes to the system is being now looked at. Hydrology, as we all know, is one of the fascinating fields, right? Because it touches on so many important things. Let's look at one by one. This definition is somewhat very interesting. They talk about occurrence and movement of water. Occurrence means where you get the rainfall and how much you receive it, right? And how it's moving from one place to the other, right? And then under on the land, meaning it can go as a river, it can also go to the groundwater, that is the underground part, and then it could be having both chemical and physical properties. What is the pH of that, what is the pollution level that we are talking about in those quantities, what is the E. coli that you have in the water body, and then what is it related to biotic and abiotic environmental components, both in the natural systems and human systems, and then what will be the effect on humans of that water. So there are a lot of connections that are leading to this science that talks about water, that relates to water, is the field of hydrology. So it's a fascinating field. Everything under that water umbrella comes under hydrology, right? But still we are, most of the time as hydrologists, we relate this to land surface part most of the time, and emphasizes on the land phase of the hydrologic cycle, but it connects to many disciplines: biology, chemistry, ecology, mathematics and physics. And then when we talk about water, many times we need to be thinking about what watershed we live in. Okay, how many of you know the watershed that you live in your own place? I know you are coming from different places. Does anybody tell me what watershed that you come from right now? I mean, don't tell the big name, like if you are from UP, and don't tell I'm from Ganges Basin. That's pretty obvious, right? Mahanadi or Krishna, Godavari, you can easily say. But I'm saying at the watershed means it's a smaller unit. So you may not know that, right? Go back to your place. Go back to your place after this class and ask this question yourself: what's your watershed? Right? That is a starting point for you to relate as a scientist to what you are looking at. You may not be studying that watershed, but I am saying on a daily basis, when you see some floods or drought news, then you can relate to real world situations. Okay? And then of course, water flows through these valleys and stream network. Climatology is another connection that we have, which is basically applied science that examines the fluxes of three things: energy, mass and momentum. If you remember these three things that moves between land, ocean surfaces and atmosphere. Let's break that down a little further. If anybody can tell me what energy is, that would help. Can somebody tell me what is energy when we talk about energy in this case? Yeah, solar, right? Or the energy that we get from the sun, how it's being used for heating up the atmosphere or water, and how the whole energy budget is managed. That is related to climatology. Mass, what is mass? Water, primarily water in this case. Air mass is also included, but water, when you talk about how much is the mass, how much is the precipitation, how much is the volume of water that you have on the ground, how it's divided between different components, water cycle that we talked about, right? So energy, that is divided from the solar energy into different components, mass, and then what is momentum? Sorry? Right, it is a movement with energy. Anything that has weight attached to that, when it moves, it's a momentum, right? Right, it's basically water. When it moves with a force, it's a momentum. Water vapor in the atmosphere, when it moves, it is a momentum. The circulation, atmospheric circulation that we are talking about, is because of the rotation of the earth, and also it's because of the motion that we are talking about from both water vapor and air, right? So these three things we are talking about: water, energy, mass and momentum. These three things are constantly changing over place and time. That is looked at in the field of climatology. Climatology connects a longer time scale. So that's a very big area, right? And then vertical and horizontal fluxes of mass. So now we are talking about not just flowing in horizontal direction. Circulation, when you talk about, it has, wind speed, when we talk about, there is a direction associated with wind. It can come horizontally, it can also move vertically, right? Likewise, water, horizontal, water can percolate vertically down. So we are talking about horizontal movement of fluxes, vertical movement of fluxes. That is also being dealt both on the land and in the ocean and atmosphere. There is also seasonal variation, the circulation that we talked about just now. And then atmospheric phase of hydrologic cycle is a climate related phenomena. Basically, hydrologic cycle has both surface connection and the atmospheric connection. There are three components that I will come to. So for now, just hold your thought on hydrologic cycle. Means it does not mean that there is only one hydrologic cycle. There is a hydrologic cycle connected to land and connected to atmosphere. Climatology, people are talking about atmospheric part of hydrologic cycle. Computational resource is very important for modern climatology, since simulation is involved for a longer time period. Whenever we talk about climate cycle, it's basically a bigger time step, right? Larger time step. So now the whole planet is divided like this, right? As you can see here, I don't know whether it's visible, but if you look at closely, these are grids, right? You have horizontal grids. Every land parcel, every land mass is basically divided into grids. And we are talking about real shallow atmosphere of 50 kilometers from the land surface. From the surface all the way up to 50 kilometers is really skinny, very small portion compared to the real, all 5 layers of atmosphere, right? We are talking about, stratosphere to all the way up to troposphere, up to mesosphere and beyond. There are 5 of them. So we don't model anything below or beyond 50 kilometers, let's say. And flights go roughly about 40,000 feet or 13 kilometers, 14 kilometers high maximum, that's all. But now we want to understand these vertical, horizontal motions of fluxes, mass, energy and momentum that we talked about in climatology for all these grids, both horizontally and vertically. If you can build a model that does all this, that becomes your climate model. That's what people are doing. So there are different models that people talk about. So there are equations, the physical processes that we are talking about, whether it is precipitation, humidity, temperature and wind speed, whatnot, and the radiation budget, energy budget, all of those things are calculated for every grid on the horizontal scale and on the vertical scale, and put together how one grid is allowing that flux to move to the next grid, how it's moving vertically up and down for every time step, for every day, for every month, every year, multiple years they calculate. So that becomes your climate model projections over a longer time. So that's the whole process. I mean, it's not difficult to understand. You probably have an idea, but climate model simulations are done at that highest level. If you break that down, these grids, into smaller units, now that is the idea. 20 years ago, 30 years ago, they started with 2 degree pixels, meaning that box that I am showing here was 2 degree by 2 degree, roughly about 200 kilometer by 200 kilometer on the equatorial region. Maybe in the northern southern hemisphere it gets stretched a bit, okay, different sizes, but on an average 200 kilometer by 200 kilometer is one box. Now over time they have reduced that box from 200 kilometer to 100, 50, 25, 10 kilometer. Right now they are breaking these cells into 10 kilometer or even less, all the way for the whole globe. You can see the computational demand that it adds up for every pixel when they break it down to 10 kilometer to simulate these fluxes for every minute in some cases. If they want to really understand the cyclones or tropical cyclones or hurricanes or floods or droughts, there are many things, right? Instantaneous landslides. So you need high resolution data. So reliable data that simulates very well considering all these processes with good data, right. So, it is a huge enterprise. We do not have a climate model currently that can do a very good job focused on India. Maybe they are coming up with one, I think, as I speak, or maybe already it is out, I do not know that, but I am just saying there are so many other models on a global scale from other parts of the world, but there is such a huge demand here to come up with a model that accommodates all this. We have the capacity, you have the capacity, but we need the kind of the motivation, the resources to come up with a plan, resources and opportunities to really put together this piece and to come up with a fancy model that can do a wonderful job, fantastic job for India or for the region, for the globe. So, hydrometeorology, what is the difference? I mean, so now I combine hydrology and climatology, that is as one discipline, and hydrometeorology, which is another field, which is basically we are talking about the mean conditions. What is the mean? The average, right? We are talking about 30-day average, 1 year average, whatever, or the higher order moments. It could be standard deviation or variance, higher moments of statistics of the atmosphere that is represented, whether it is for precipitation or a temperature or other variables on different time steps like daily, monthly, annual scales. That is the traditional way of thinking, that is actually hydroclimatology or climatology. But now people are saying, no, when we are talking about average conditions over a long time, that is climate, it is not meteorology. So then what is meteorology? They want to combine hydrology and meteorology over a shorter time scale, right. So that is the difference between hydroclimatology and hydrometeorology. Coming to modern climate system, we are dealing with this planet Earth at 5 spheres. For 5 spheres, there are this energy, mass and momentum that is moving across this whole globe, considering atmosphere, cryosphere, lithosphere, biosphere and hydrosphere. These are 5 spheres that we need to understand. We are connected to hydrosphere, atmosphere, but we are not so closely connected to cryosphere. But lithosphere means, I'll have to explain one by one, right. Atmosphere we know, anywhere from surface to up to 50 kilometers. Cryosphere, these global Arctic masses, ice mass, glacier mass, those are cryospheres. Lithosphere is the soil below up to 2 kilometers. Biosphere is vegetation that we have on the ground. Hydrosphere, anything related to water, the river, lakes, ocean, all of those things are connected to hydrosphere, right. So these 5 spheres are constantly linked up in climatology, but in hydrometeorology, basically we are talking about the relationship between the atmosphere and the land phase of water, very closely connected to atmosphere and land surface of water, land phase of water. According to NOAA's 1996 definition, but the distinguishing thing about hydrologic cycle is this. When we talk about hydrology or terrestrial hydrologic cycle, 3 things that I talked about: inflow, outflow and storage, right. So what is inflow? In this case, whatever we get and whatever we let go is the outflow, and whatever is remaining in the area is the amount of storage, right, whether it is in the land or in the ocean. In the atmospheric bank, that is for the land surface part. For the atmospheric branch of hydrologic cycle, we are talking about precipitation coming from the sky, evaporation and the atmospheric transport of water, right. That is the atmospheric hydrologic cycle. So you can clearly see the connection there. So precipitation, right, is the kind of inflow, outflow is your evaporation, and transport or storage. Atmosphere doesn't store, it's basically transport from one place to the other. Cloud moves, water vapor moves, all of those things, right. So that is the storage in the land surface, the transport of water in the atmospheric side, right. But there is one connection between terrestrial branch of hydrologic cycle and atmospheric branch of hydrologic cycle, which is water. where is that water coming from? Evapotranspiration, ET, right? So whatever we have on the ground as vegetation, right, they are supplying water to the atmosphere as evapotranspiration. So the loss for the land surface as ET becomes the gain for the atmosphere, because they get that water from the land to the atmosphere. And what is the loss for atmosphere in this case? Can somebody tell me? This is the quiz. I talked about the loss for the land surface because of evapotranspiration. What is the loss for atmosphere? Very good. Precipitation. I am glad that you are with me. So that is actually losing that water to the land surface. So that is the loss for atmosphere. So that loss, and I mean, if you ask an atmospheric scientist, they will say precipitation is a loss for us. But for hydrologists, the life starts from precipitation, because that is the source of life, that is the source of input for us. So depending on the discipline, you can see one calls as a loss, one calls it as a gain. That's an interesting thing to observe here, right? So now quickly, two climates that we are talking about. In the past, people are talking about climate is the dominant one. They ignored the landmass, right? They talked about anybody pre-1960s, if you go, they'll say, oh, this planet is relying to only based on the atmospheric conditions, we need to decide everything. But people on the other spectrum, the climate of the second kind, said no, just don't talk only about atmosphere, you have to include the land surface also as part of it, because now you saw the connection, right? What we are losing from the land is the gain for the atmosphere as input. So what they lose is the gain for the land. So there is that connection that we already have. So this is the new kind of climate that we should be considering as climate of the second kind. Climate of the first kind, people always close-minded, thinking only about atmosphere, but climate of the second kind said we have to be little more broader, combining both land and atmosphere. That's how the field of hydrometeorology and the connections between land and atmosphere that came together in the post 1960s and post 1970. That is the end of it. I'll stop there for questions, and then maybe we can have a 5-minute break, and then I will continue on with the next interesting part. Any questions that you have on those? This will go really quick, the next one. But we have 45 minutes to go, but I can take a break if you want. What do you think? Okay, we can take a break. Okay, so let's assemble back here by 11 or 11 minutes. 12:11, sorry. Papers I am presenting are showing here not to discuss in detail, but for you to probably read for your interest if you have time. Later on, download, keep them, or if you need them, send me an email, I will send the PDF for you. One is, these are the hard-working students, from IIT Kharagpur and other institutions have performed over the years that I was fortunate to be part of, and I am presenting here. It connects to these extreme events. That's why I wanted to bring this. So I don't want to repeat too much because it's already a published work, but it might give you an idea. You remember this morning we talked about extreme events, right? Where we divide this country into multiple regions, right? Here we are talking about, I don't know, it's west central to peninsular India, here to northwest, central northwest, northeast, right, like that, different regions, and you can see big cities. There are 19 cities or so that we looked at, and then Z values from Mann-Kendall test that we are talking about here. We have annual rainfall, monsoonal rainfall, 1-day maximum rainfall, 10-day maximum rainfall, all these indices that you just talked about this morning, right? And this paper we looked at some 7-8 years ago for different cities: Kochi, Coimbatore, Kozhikode, Bangalore, Hyderabad, Pune, Mumbai, Surat, Nagpur, Kolkata, Indore, Ahmedabad, Bhopal, Patna, Kanpur, Lucknow, Jaipur, Delhi, and I think Ghaziabad. So those are the 19 cities we looked at, and we come up with what kind of trend that we have, increasing or decreasing trend with respect to annual rainfall or monsoon rainfall or 1 day or 10-day kind of rainfall. There is kind of a mixed signal that we got, but many cities are looking at increased 1 day rainfall or 10-day maximum rainfall. And there is also some cities that are showing decreasing monsoon rainfall, and many cities are showing decreasing annual rainfall also. So it's a puzzle, right? We don't know what's going to happen in your own town, in your own city, and we want to constantly evaluate. This was using the historic data from IMD, Indian Meteorological data for 1901 to 2015, basically about 115 years of record that we have. We calculated all these metrics and we came up with this analysis by cities as well as by basins. And the red color, actually what you see as increasing tendencies and decreasing tendencies as green color between 1901 to 2015, and then we divide. You remember I talked yesterday about pre-industrial, post-industrial. I mean, there is some level of arbitrary nature there for dividing this time zone, but looking at pre and post-industrial, let's say 1970 and after, in the last case, more of red, extreme precipitation that we are seeing here magnitude wise, and this is 95 percentile and the other one is 99th percentile. You can see most of the country is red in color, meaning increasing extreme events of 99 percentile, the tail that we talked about today. That's what I am trying to connect here. This was done on a larger scale for India, and we are clearly looking at based on the historic record. If somebody questions what is the integrity of this analysis or models, we are not using the model. This is reanalyzed or reanalysis data or remapped data of IMD's point data, gridded data that we talked about this morning, Dr. Venkat Reddy presented. But then we looked at the basins. There are about 23 basins or more that we looked at, and we found out consistently 99 percentile extreme precipitation events over the last 115 years have gone up. That's worrisome. That is the reason why we are having this class, to look at how can we then understand the impact of this extreme rainfall, what can we do about it, or how can we improve this analysis even to better predict into the future of all these extreme events, right? So there is a connection there. One other add on to this kind of extreme analysis is drought. This is a separate paper that we did, but it includes both the past conditions and also the future. Now you got a taste of climate models, right? We talked about climate models. This used, I think, even CMIP previous generation data set, version 3, I guess, or RCP, that is CMIP 5 versions that we used here. Historic is here. We remember that same timeline that we talked about, 1976 to 2005, and both for IMD as well as the forecast or reanalysis data that we used. So the other thing is, for the climate models, RCP 4.5, we used RCP 8.5. That is the middle ground scenario and the extreme scenario. Yesterday map that you remember, if you remember the discussion that we had. And if you look at first 30 years, or between 2030 to 2040, 2010 to 2040, 40 to 70, 70 to 2100. This is basically the duration. We are talking about months of drought conditions that are prevailing in North India, Central India, Western India. The number of months from 3.5 to 4 months are increasing. That's a huge number. 3-4 months of drought for a bigger area like India, it can create lots of problems, right? I mean, if it really happens. So that's where, I mean, this is done with the previous generation data set, but there can be newer analysis that can really tell you more or improve these results to understand better. If you go further down RCP 85, the worst case scenario, lots of red, lots of intense color here. So that's the part that people, policymakers, managers should be considering. One is the duration, the other one is the occurrence. What is the occurrence? How many events that you will see between those times? You remember we talked about CDD as an example. How many dry days, consecutive dry days that we have for a given number of events. So we talked about 10 or 13, 20 events that we have seen. So here in this case, one such example is about 160 events that you will see for RCP 4, 5 into the future 30 years time frame. More number of events that you will have. It could be shorter events, it could be longer events. I mean, when we talk about drought, there are varieties of droughts. Meteorological drought is anywhere from few days because of lack of rainfall. We are talking about 3, 5, 7-day drought, 10-day drought, maximum 1 month. But when we are exceeding to agricultural drought, I mean going to the agricultural drought period, which is about the growing season time, 3 months, 4 months time period. And then hydrological drought, which is probably even multiple months or even years because of stream flow that we are talking about used for drought predictions in hydrological drought. So here the events that we are talking about is meteorological drought, if I remember correct. 160 such events are happening in the highest level here for worst case scenario in the future. So that's a worrisome condition for us to consider. How can we do better with respect to predicting and understanding and implementing some adaptation strategies for water management. So again the same thing, extreme events 95 percentile, 99 percentile for magnitude as well as number of events. Red events that you see here for 99 percentile, almost the entire country except the upper parts of Godavari you can see, and the southern tip is having some declining trend, but most of the country is red. That's another interesting dynamic here to look at. This is based on the historic times, right? This is observed data, not models. So there is more reliability, there is more confidence in these things. And then in the future, again, you can calculate this maximum rainfall 1, 2, 3, and 5 day. For different windows, again, the whole period or the first period and then the second, maybe this is a whole period, first and second period. And you can see mostly they are all showing increasing rainfall, maximum rainfall of daily. That means you are talking about more floods in cities, more floods in areas that are already developed, that will have less chances for holding this water. That's causing more problem. I mean, rainfall is one thing, but flooding, when we talk about how we modified the landscape, is also adding problems to that, right? That's adding impervious areas, minimizing the time for percolation, allowing quick runoff, flash floods happening, and the elevation of the city that changed because of constructions and everything, that can also have additional effects. That will come into more on the hydraulics and flood side of modeling side, but precipitation as an input, if you look at the increasing trends of daily maximum rainfalls in the future, or this is for the past conditions, but the trend that we are looking at into the future also is more, which may be a problem. These are the papers that you can refer to, download them later and read for your interest. And again, I'm going to actually show this report, which I liked very much, which talks about just the 9 months of 2023 from Center for Environment in Delhi. They came up with down to earth report, which is wonderful. I mean, they start talking about defining extreme events. Somebody asked about how do we define an extreme event, or whether or not this event is related to extreme event or not, those kinds of questions that we asked. But they actually adopted a definition aligning with Indian Meteorological Department. There is not a single definition, but there are classifications and thresholds published by IMD. What are those classifications? We are talking about extreme events in this case are selected by IMD and CES in this case, lightning, heavy rainfall, heat waves, cold waves, snowfall, cloudburst and cyclones, and others they call some other stuff. So lightning kills a lot of people. I would call the time scale here anywhere from few minutes, few seconds, few minutes to few days, not more than that. All these extreme events that they are bracketing. So extreme rainfall, if you look at, they call anywhere from 64.5 millimeters to 115.5 in 24 hours, which is roughly about what, 2 inches, 2.1, 2.2 inches to 4.2 inches, which is basically within 24 hours going to be a good amount of rainfall for these developed areas to follow. Very heavy rainfall, anywhere from 115 to 204, and extremely heavy rainfall of 204. You are seeing that during this monsoon season, whether it's Hyderabad or Mumbai or many other cities in the middle, we are talking about extreme rainfalls of greater than 200 millimeters, right? We don't have opportunity to store them, to allow them to percolate, and they runs off on this impervious land and creates lots of flooding issues. So that's the kind of scale they are using here, called extreme weather events, EWEs. Heat waves, anywhere, departure of 4.5 to 6.4 from the normal maximum temperature, and severe ones would be more than 6.4. And cold waves or cold days, they call temperature drop of 4.5 to 6.4. Cold is greater than, severe cold is greater than 6.4. Mostly applies to North India in this case, North and Northeast India. Cold wave, minimum temperature drop of 4.5 to 6.4. Cold wave, severe cold wave would be greater than 6.4. Snowfall again confined to 3 states in India, Jammu Kashmir, Himachal Pradesh and Uttarakhand to some extent, but not many other states. So, and again they don't call it extreme events unless there is no death, unless there is death. Cloudbursts are happening in Uttarakhand and Himachal Pradesh and some extent in Jammu Kashmir. Cyclones, there are events that we are connected to in this region and many other parts also in western coast. Anti-clockwise mostly in northern hemisphere because of the rotation of the earth, Coriolis effect. Here we are talking about clockwise direction, and I will talk a little bit about the speed of the cyclonic twist that we are seeing is changing because of climate change for India, and how it's changing the rainfall later. I will come back to that later. But these are the extreme events. What do you miss here? Can somebody tell me? I just wanted to ask a quick question. On these extreme events, we talked about some other events also, but one thing that is missing here, based on the CES definition. What extreme event is missing? Droughts. Very good. Good catch. Why is that missing? Is that not an extreme event? I just talked about previously in one of the slides that for India we did the drought analysis. Why is that not considered as an extreme event? Right. That's the reason. The time scale, I think, the logic is not clear to me here. They are considering anywhere from few seconds lightning to few hours to few days, not more than that. But drought starts from short term of drought, meteorological drought, few days. It can come in extreme events. That's what we studied before, and it can actually extend beyond few days to few months, right? The occurrence or duration that I talked about going up to 4 months, right? So it is kind of that blurring line between calling it as an event versus a disaster. So I think there is that fine line that they are thinking, or I'm not sure, that can be considered like that. A disaster means probably, landslide is also a disaster, but it's included in this extreme rainfall. Anything that, exceeds certain amount of rainfall, they say landslides are possible. But droughts are not called as an event. which may change over time, but something to think about in the future. So again, the rest of them are extracted from the report. In the interest of time, I am going to skip all this because you can read yourself. You know, most of the region in India are seeing extreme events, and within these 365 days of the report in 2023, they found 318 days on an average. You are getting one event or more in any part of India. So that's an interesting statistic to me. You know, I feel like it's an important number. And then 300 or 3,300 people are dying because of this fatality every year. That's a big number. You know, as engineers and scientists, we have the responsibility to minimize that loss or make it to zero. How is that possible? That's where early warning systems comes in, infrastructure comes in, resilience infrastructure, to understanding and you know, coming up with better tools to predict floods or droughts. All of those things combined minimizes the loss of people and also properties, livestock and infrastructure and so on and so forth, right? So there is a connection to all these things, but this is an interesting slide that I wanted to discuss. It's not from me, I show the source here, but what you want to understand from here is this, the land surface atmosphere link and the feedback that we are talking about. Somebody asked this question, so I ask you to wait, Satyanarayan Swami. So we can see here, present condition, what we are looking at is the cycle, water cycle or whatever you call that loop. You know, here evaporation, right, it happens and it brings moisture. The circulation, actually this is atmospheric circulation, evaporation that actually moves to the land, brings precipitation, and land mass is warmer because of the land, I mean the solar heating conditions, it really warms up the surface, right? So that is today's condition. Today or this season or last season or probably next season, you are seeing like this, present day. But what's happening in the future? You have weaker circulation. On a global scale, the whole movement of mass, energy and momentum that we talked about before, causing the circulation is weakening for some reason, which we need to really verify for India whether or not that is the case, but many reports suggest that it may be the case. If that happens, added to that you have increased heating both from the sun, from for warmer land, as well as increased air temperature causing more moisture evaporation from the ocean surface, brings more moisture. That means we are talking about more rainfall. So there is a connection to climate as well as climate variability as well as climate change in this particular slide, past and future, but this is the future here, right? So we are expecting more rainfall just during the monsoon season, and India, maybe more than 70% of the land mass gets rainfall from these monsoons, whether it is southwest monsoon or from the northeast monsoon. The periods you are familiar, right? The southwest monsoon is from, what is the period? Can somebody tell me? June to September. What is the northeast monsoon cycle? October to December, or probably end of November, whatever, that 3 months roughly about. So except coastal southern part of India, many regions are benefited by southwest monsoon, the other regions are benefited by northeast monsoon, right? So these are the two different systems that bring, and both are really coming, are having the circulations impacted by this climate change, and that's going to really add to already created warming conditions in the atmosphere. We are not talking about the warming conditions on the land here. So what happens to the increased temperature from this vegetation, biosphere, under changing conditions? There will be more ET, right? If you have enough rainfall from here, from these monsoons, we are talking about more evapotranspiration and evaporation from the land mass that will probably give more rainfall. So the urban heat island effect, that what we talked about before, the heat mass that goes up and then we have all this moisture that's moving in, bringing and dumping this rainfall. One other understanding from all these climate change studies is that because of increased temperature in the atmosphere can hold up to 6 times more moisture of this movement from the ocean as well as evapotranspiration that we are having. So, the drier column in the atmosphere is more, that means they can accumulate more moisture, and then when they move to a certain place where the condensation can happen, it dumps all that 6 times fold increased rainfall amount. That's what we are talking about. So, that's why we are talking about floods that's happening from the atmospheric side. But if the land mass is not really disturbed by the humans with all these built up structures and all that, we are talking about damage to an extent, but not to a great extent. But cities are flooded because we are already changing the landscape that's causing the problem. So, this is the connection that I am talking about between both land and atmosphere as well as climate change, and also looking at how the atmosphere holding extra moisture is dumping this rainfall. So, these are the physical reasoning behind what we are looking at as extreme events. The red maps that I showed before for the past times and also into the future is the combination of all of these physical processes that's happening over the land mass in India or probably in other parts of the world. So again, we are expecting for India to be having at least about 5 to 10% increase. That's a big number when we are talking about during the monsoon season, about 850 millimeters of rainfall that we are seeing as an increase, right? So, that's a big number, and the variability is also there. When you consider both variability as well as the increasing trend of 10%, it's a big number. It can impact agriculture, especially if it floods. I don't know if you remember, recently I saw some of these paddy fields in India, whether it is Tamil Nadu or central India, I forget, but the farmers were impacted because of heavy rainfall during the monsoon season that flooded their crops. So, that is probably is going to happen. It's not just the urban areas that will be flooded in the future, but if it floods even the agricultural areas, food security becomes an issue. Now, you can relate SDGs to temperature increase, to extreme events, to flood, and then producing less food, crop yield is affected, hunger, which is your SDG 2, zero hunger, that's going to be not met by 2030. So, you see how the connection is established with one particular event, one particular variable with all the global things that we are talking about here. So, that's the kind of connection you should all establish anyway. Now, coming to this regional analysis, this report again you can read later, but they divide by region, the whole country, and then they talk about how many events that all the 9 or 7 events that we talked about, they are coming up with the numbers, and then how many events on a daily scale, whether it's heat wave or cyclone or extreme events, all of those things they talk about in 1 year during this time, extreme weather events in India for that particular duration from January 1st to September 30th of 2023. I think they are coming up with the every year report. So, you may be interested in downloading the future reports, and maybe you may find opportunities to work in those kinds of places if you have fancy ideas coming out of your research that you think you can help improve the understanding. So, the seasonal analysis is done for different seasons, winter, pre-monsoon, monsoon and post-monsoon. They come up with how many events that happened on a country scale here. So, I will kind of skip all this. So, they show on a map how many events that happened, like lightning for a given location, and they kind of total them up. For every event they say like heat waves, extreme events, cold waves, snowfall, cloudburst, cyclones, right? And then they are establishing the connection. There in the one of these reports they are talking about drought. They are connecting drought also to climate change, but in case of that Center for Environmental Science Analysis, they actually did not include drought, but I am assuming they might consider in the future, because shorter duration droughts are also possible still, they can consider. And we are talking about extreme events for India there are many ways that science can contribute to better understanding. This is another case study. I think Dr. Venkat Reddy talked about it previously. These two watersheds for extreme indices, right? Several indices that we calculated. We took that exercise further down by building a model to predict flooded areas. This is not a great outcome yet, because we have to really improve our modeling skills, connecting hydrology to hydraulics, and come up with flood area inundation maps. So the the same watershed, Nagavalli and Vamsadhara basin, and then we looked at what is the inundation depth. The data is very scarce. We don't have the data to validate this kind of models, but we kind of quickly came up with a framework to establish climate, looking at hurricanes, how they move into this area from Bay of Bengal or tropical cyclones, and then we looked at increased rainfall, and we took 7 or 8 events of those rainfall events, translated that into flood hydrographs, used those flood hydrographs into HECRAS models to come up with flood inundation areas. We don't really still have flood inundation depth, I guess, but we were just showing what areas are affected, and then we extended this to say they can use this for real-time forecasting through web interface here. They can also use some of the model outputs. I'm not sure whether it is still live, but at that time when the project was going on for 3 years, we came up with this outcome. The next one I wanted to show you just as information in the last few minutes before we conclude is this Himalayan glacier. How many of you have heard of the Chamoli disaster that happened in 2021, February 7th of 2021? I know somebody is from IIT Roorkee. Did anybody hear that before? Have you heard of this incident? Okay, good. Yeah, so I think in one of the slides I will have, there is the huge glacier collapse that happened. Yeah, here. That glacier mass that suddenly collapsed, it's about 15,000-16,000 feet altitude, higher mountains, and it's close to China border. I visited this spot 3 years ago. It's about 9 hours from IIT Roorkee. We 17 people went there. We looked at how this collapse actually carried water in the Ganges, and it really flowed through this all the tributaries, Rishi Ganga, Dhauli Ganga, and then through Vishnu Prayag area. It went to Joshimath, and the areas that we looked at, these are the places where we kind of flew drones, and we looked at how this drone we were flying, and then we kind of used the segments to calculate flood inundation areas. Used hydrology models, and Tapovan is the hydropower plant that got destroyed. Some 75 to 100 people died in this particular site also. It's an extreme event analysis. I'm just showing this as a case study that I did, but I did not finish this analysis. This is something that one can take up further to really look at how to quantify what was the loss of ice mass or glacier mass that we had from that uphill portion, and how it got carried, how it moved through the system, and then it did not go further down. I think the energy got dissipated downstream. It did not really propagate further down after Joshimath or somewhere, or maybe they stopped the flow, but the water height went so high that it even removed some of the bridges, strong bridges. And I took some pictures also. I don't know whether I have them now, but I will show at some point. But it's a fascinating place. There is science to be done in this case. We kind of did the limited analysis using SWOT model, which is not an event model, but we went ahead and we came up with converting rainfall into runoff, and then that is an event model, right? It happened in few hours. So we are just using hydrology model to understand what is the average annual rainfall or precipitation to runoff relationship. So the main idea here is to introduce you to the concept of extreme events in today's class. I will actually show you a little more about climate. I'll introduce the idea of the last few minutes or first few minutes of tomorrow's class, talking about the connection between climate variability and climate change. But I just want to provoke your thoughts right now. Can somebody tell me what is the difference? What is climate variability and what is climate change? You know, as a faculty. Very good. Yeah, that is the point. Climate variability is talking about a longer time period, and again, it's also talking a little bit about the past conditions. Climate change is primarily related in the context of future. It's also longer term projections, but climate change in the context, people normally talk about future conditions. And of course, precipitation, evapotranspiration, interception, soil moisture, groundwater storage, and stream flow is the driving force, as we know, in hydroclimatology, and they provide the connection to water resources management. And if you look at the time steps here, this is an important one: days, months, years, decades, and centuries. Climate change looks at century scale. Climate variability looks at decades to multiple years. Seasons are generally in months, days are weather events. So we are talking, your discussion this morning was centered around weather, but we kind of looked at seasons to climate variability and climate change in the last 2 days of lecture, generally talking about what happened in the last 100 years, what happens in the next 100 years, you know, for a given region, and specific events that we looked at. And you know, it can happen in days, seconds to minutes to hours to days, weather events, and in many cases some of these disasters that happens on a climate scale. So a kind of a nice illustration and saying the connection between, or the distinction between, climate variability and climate change. I will stop here, but I think we are very close to kind of wrapping up this text and then talking about land atmospheric interaction and how it leads to flooding discussions. I think that's the connection that we can easily go from here to tomorrow's class. Before we close for today, is there any burning question or sticky point that you have in your mind that you want to clarify now? If not, certainly up to this point, whatever is presented, we will post the material of these slides as well as the PDF of the documents that I extracted these graphs and reports from, that you can keep for your reference. You don't need to read them thoroughly now, but at least when you go back, if you want to kind of refresh your memory and relate to what you are doing or pursue something different from what is done already, those things can happen based on the discussions that we have here today as well as what we had discussed yesterday. I'll stop here. Unless you have any questions, I think I don't want to stand in the middle between you and the lunch. So we'll, no SWOT model for this session, because I think we will have HMS, event model, and we will have HEC-RAS, I assume, and then we will talk about machine learning models little bit on the last few days, because we did some neat stuff. Google Earth Engine based analysis also will show you, land cover, land classification. I did some work on machine learning integrated flood forecasting. If anybody is interested, we can discuss that later on, but that's not part of this class anyway, not to go in that depth actually. Okay, all right, I'll stop here. Okay, I hope you get some energy, some rest before coming back at 2:15. We will meet at the same place like yesterday and go from there. Okay? Okay.
Okay, I have already uploaded the tutorial of day 2 in the group, so you can download that. I hope everyone have installed Jupyter notebook that is kept ready. So So, if you haven't installed Jupyter Notebook, you can use any of the systems. In the systems, the Jupyter Notebook is installed. So, Okay, I have uploaded a drive link. So you can download the shapefile from that. If you access that drive link, you can see shapefiles. Inside that, just you can download shapefiles itself. That folder. Inside that, we are having Hanumakamba shapefile. Is everybody able to access the drive link? So actually here we are going to work on 10 climate indices. So there will be 5 precipitation indices and 5 temperature indices. So you can see in the tutorial manual. So this particular this exercise is going as per this methodology. First, we have to install all the required packages and import them. So, and then it is like we have to take the data from IMD, then extract the points, then we have to calculate the climate indices, like these 10 climate indices we have to calculate. We have to specially interpolate these values and then we will visualize this data. This is the complete exercise we are going to do. So I believe everybody has opened Jupyter Notebook. Yeah, so then we can start now. So here, in the tutorial itself, in step 1, you can see I have commented the installing the packages. So some it will be installed already, that's why I have commented that. So you can write the code pip install and install numpy pandas that are normally available in some Jupyter notebook. So you can give all this X-ray, BioXarray, GeoPandas, IMDlib. IMDlib IMDlib is is the package which is used to download the data from the IMD directly. That is a Python package. Then next, PyManCandle is used for ManCandle test. So today we have, like in the first session, we have came to know about the ManCandle test. So which helps to analyze the trend across the region. So that that can be called with the help of PyManCandle. That is the Python package. Then a rastrerio is to take the rasters to visualize the rasters. Then others, Folium manual is for interactive map. That will be all used for the visualization purpose, matplotlib. So you can use the first line. Just type the first line. Don't just copy paste it, type it. Okay. I will start from the beginning, okay? So take the Jupyter notebook Okay, everybody please listen here. Okay, now first we are gonna create one new folder. Okay, new folder day 2. Inside that again new notebook. Okay, here new Python 3. This one notebook. This will lead to this one. Provide a name. Okay. Now I have provided the code. Just type pip install numpy pandas x array. Okay, this x array is used for taking the IMD data in array format. New x array. GeoPandas. GeoPandas is visualizing the spatial data. IMDlib. IMDlib is used for taking the data from the IMD. Pyman Kendall. Rastrio. Okay, these are all are installed already in mine, so that's why I've commented. Mostly people might have all this in them, mainly, but this IMD this and all will be new. So then just import this libraries. There is a couple of libraries. Okay, I have told you to download this one. How to download? Just only this shapefiles folder I have told you to download. If you go to that link, that drive link, you can give download here. So download like this. And extract this folder to the folder currently we are working on. So extract directly to there itself. There should not be change in the path. So you should extract that folder. So you can see that here. This is the currently we are working on. This is our IPNB file, Jupyter Notebook file. Here it is showing as shapefiles. Inside shapefile we can see six. This is the shapefile of Hanmakonda region. Okay. Next, we have to import this many libraries. So you can paste that here. Have you finished installing? Everybody? This is a simple line, one code of line. Everybody, that's it. Finished, right?
Ask them to raise hands if they're still needing time.
Yeah. Anybody require time, they can raise your hands so that I will know. Yeah, okay, fine. So make sure that you are doing this inside a folder itself, because it is very important. All the results will be going inside this folder itself. You can see in the later steps that we are defining the paths inside this particular folder only.
For whom?
If I add in a demonstration, we should have done that on the start. And only they can do this one by default is 3.13 in general. The base is 3.13.
That is fine. You can run.
No, not all libraries you have computer with that.
नहीं इधर और नहीं बस पेपर वन रहा
3.1 is on.
she is getting 135
But you are getting 3.13.
Yeah.
regarding matter only after
Okay. Okay, now this is like we are defining the. Okay, this is now we are like defining the grid point. So we know that Hanmakonda region lies around the latitude and longitude of 18 degree and 79.58 degree. So with this we have to take the IMD data for rainfall points and temperature points. Here actually it is like just in rainfall it is 0.25 into 0.25. Rainfall points are 0.25 into 0.25. So as per this code it is like it is going, you can see the range -1 to 2. Yeah. So this code will run where this particular 3 into 3 grid will be formed for the rainfall points. And in temperature, this is for temperature, sorry, this is for rainfall. Temperature is 1 degree by 1 degree. So that will be same, it will run the code again, and here it will take as it is sparse, like the distance between the points in the IMD data is far, only 6 points are taken. The first 6 points while iterating. Now, this is the shapefile path. Since I have already said to you guys to download the shapefile, here you have to, I have already said that to work on a particular folder. So this is a folder I am currently working on, and you have to put your shapefiles which we have downloaded from here. Here you can download from here the shapefiles, and after downloading you can extract that shapefile data to this particular folder you are currently working on. So this shapefiles, just check that it is inside having all these 6 files. Hanmakonda region it is. We are currently working on Hanmakonda regions, and these are the points which are lat longs which are given for Hanmakonda region. So make sure the name is shapefiles. We are calling this shapefile path, like we are giving a particular name for this path as shapefile inside this folder, shapefiles Hanmakonda SHP. Okay. Have you everybody finished till shapefile loading? Till the shapefile.
നിങ്ങൾ ഈ നോട്ട്ബുക്ക് എവിടെ സേവ് ചെയ്തിട്ടുണ്ട്?
Surya.
Okay, next one. These are I'm defining the output directories. So here IMD data we are going to download and that will be saved in this particular folder. Okay. So use this part of the code also to avoid the projection errors. Since there is we are dealing with both shape files and also raster file. the next part of the code. So this was the step 1, installing the required packages. Next we are going to step 2, where we are downloading the IMD data.
You want to check if everybody is able to run it?
This is just only giving the name for step 2. So next we are dealing with this part of the code. So here you can see variable start year, end year and output directory. Here we are having 3 types of variable: rainfall data, T minimum and T maximum. I told about already rainfall and temperature data. If you are manually going to install this, we will have manual download like this. It is really time taking, but wait a minute. Yeah, each year you have to give separately. Here in graded data archive, rainfall data, and when it comes to temperature minimum maximum, same is the condition. Here we have to give the year, we have to download each one by one. But with the help of this code, particular code, you can see here, this part of the code. Here what is happening? Yeah, you can see here. This variable will take rainfall, temperature minimum, temperature maximum, and we are giving the start year and end year, and this output directory we have already defined here as IMD data. So this is the function. This is the function we are defining.
അല്ലല്ല അങ്ങനെയല്ല ഷിഫ്റ്റ് ഉണ്ട്, ഷിഫ്റ്റ് പ്ലസ് ഉണ്ട് എല്ലാം ചോദിക്കാം.
Okay. Okay. So since it is actually with this particular code we can run and we will get the IMD data. So how to do that is, okay. So you have been provided by a link where we can manually download this IMD data. That is by click on that link. When you go there, you can see under gridded data archive. Under that, you can see rainfall 0.25 into 2 pi binary. Click that. Then you will be directed to this particular screen where we have to download each data. Now we are currently required of from 1981 to 2020. We have to download that much data. Think about downloading each data one by one. It will be very difficult. So this same applies for the maximum temperature. If you click here maximum temperature, you will get to download each data one by one. Same minimum temperature also, one by one. Instead of that, this code is used. You can see in this code, just we are giving the start year and the end year and the particular variable. That is, if it is rainfall, then we will take the rainfall. If it is temperature minimum, it will go for temperature minimum and temperature maximum, like that. This is a function. This have been just defined here. Now we have to run this function. Execution of the function, we have to type that code. So you can ref main download data This is the execution of that. You can see that it is downloading the data. So how this is working? So we are calling this particular function download IMD data, and we have given the variable rain instead of the variable rain, and the start year 1981 and end year 2020, and the output directory. You have already mentioned the output directory here where it should be saved, IMD data. So you can see here inside the particular folder, I have specifically said we have to work on particular folder only. This is because it goes and saves under this as this particular output folder, IMD data. You can see it is getting downloaded, 1981. Okay, I will repeat once again. So you can see here. Now what I have done is, this is the function which I have given. This function directly I have given, and I am executing this function with the help of this code, this small code, where we are calling this function download IMD data, and we wanted rain, so I have given rain, and 1981 to 2020, and output directory as this one, which I have mentioned here. So we will get it as IMD data rain. The files will be saved here. So it is currently downloading.
So I think one thing you want to listen, it will take time for you to download IMD data. So I think Surya is planning to give you the data. Now you know how to download. You don't need to wait for that to be done. So that you will save time. Is it okay? I think so. Look for. So how many of you have already downloaded? Yours is done or is still going on? Raise your hands if you have already downloaded. Only one, two. Okay, only two. So I think they can copy from the folder that you do, right? So,
Okay. This is the execution of the code. Now currently I am stopping this. I will provide you the data. Here you can see now IMD data. So here inside IMD data, what we are going to do is that I have given already the drive link, right? So stop. I have interrupt the kernel. here I have made this code to a markdown just let it be there. Okay. With this code, we will get the download data. Instead of that, go to my particular drive link inside IMD data. You can download these three. So, download IMD data. Go like this. Download. Let it get downloaded. While this is getting downloaded, we can take a snacks break. Okay? This one. Keep that for download and we can go for a snacks break.
Are they going for a coffee break now?
Okay guys, like you can put this for download and we can go for a snacks break. Take a break. Okay, can we start? Okay. So I told already we can download with this. Instead of that, I told to download from the Google Drive. So I believe you have already downloaded the data from the Google Drive. So I will direct you uh, how to paste in the particular folder itself. So you have downloaded from here. Click here, download. You will get empty data. Then what you have to do is go to the downloads and extract this. Extract this. Yeah, here I am the data. So these three, I'm copying it to the folder which was I am currently working on. So that was, you can see here in Aamhe data. This is the folder I am currently working on. Go to your folder. Day 2. Here, IMD data. Delete this. It was like we downloaded a little bit, and instead of that, drag this and put it inside. So we will get the grid data for 1981 to 2020, complete data. So I will explain once again. This is like, go to the drive, download IMD data here, it is already given here, download, and extract the data to some place else. Go inside that folder, you will get the rain temperature minimum and maximum here, like this, and just paste that to the working folder, currently working folder. Inside already one one folder will be created. Delete the before one and paste this one. And check from 1981 to 2020, every data is available for rain, temperature minimum, temperature maximum. Okay? Be careful with the names of the folders. If you are changing any name, change accordingly in the code also. Yeah. So now we'll go for the step 2. Step 2 is extracting. I have set already there, like rainfall points, temperature points. So we just downloaded the data for whole India region from 1981 to 2020. But what we have to do, we have to study for the area of a region which we want, that is Hanmakonda region currently. So that particular points we have defined here. So with the help of this code, you can see retrieval of climate data using Python. Here, def extract grid point. Please take this code. And run this code. Yeah. Here you can see extract the grid point data. This okay. Some people have doubt again in this. You have to go to your the drive link I have provided. Go there, download IMD data. Just click here this download. You will get here downloaded. Then extract that data to the folder you are currently working on. So I have given day 2 here. Go to that folder. Inside that already, if you have run that code before, IMD data one folder will be created. Paste this rain, T minimum, T maximum inside. Okay, moving to next step. Next is extracting the grid point data. So we have whole India region ki data here. But what we want is, we want to extract only the particular Hanmakonda region. Here it will search for the points like the lat long, and in IMD data it will search using this particular function. It will take the data in particular lat long. So give this function. Now again we have to execute this function. This is not extraction. This is just we have defined the function only. Now we have to execute this function. Here the execution step. This is complete execution step. Just we have to do is now data extraction. You can see here we have downloaded the data that I have. That is not required. Now data extraction. Remove this part and run this. Only second one is required. You can type this. This is basically calling this like load all the climate data. Here we have given load all the climate data. This function we are calling. Then we are extracting all the grid points. All the grid point data. That is extract all the grid point data. That is rainfall, temperature minimum and maximum of that particular lat long. In the IMD grid data we have downloaded. Then we are saving that as CSV format. We are saving that. This will take some time. Okay. Now this has finished its. You can see one more new folder has been created again. That is extracted data. Inside the extracted data we are getting rainfall grid data, temperature maximum, temperature minimum. Here all the grid point data is there. This is the combining of all this data, that's it. You can see here from 1981 day 1 to 2020 December, that much data, each data is downloaded. That too, I've told you already, like temperature minimum maximum and rainfall. These three we have to download. In that, this point we have already defined, and for that every from first to 2020 last, that much it is downloaded. Okay. I will explain how to paste this code again. First, go to, this is third one we are doing, extracting the particular Hanmakonda region only. Take this particular part of the code to extract the grid point data. This contains till saving the CSV folder, and this particular part of the code. Then execution part, this is the execution part. that is coming on different page. It is given as a complete code here, page number 12. Here, this part of the code only we are running. We can visualize what we have downloaded, like which coordinate region we have downloaded. Then you will get an idea. This is visualization. You can see here, these are the rainfall points on Hanmakonda region. The blue color is the rainfall points. This is the next part of the code. And this is the temperature points, temperature minimum and temperature maximum. This is what exactly we had downloaded from the IMD. We visualized the IMD points which have been extracted. Next step is to calculate the climate indices. Just here, as the time is so far, so you can do this as a homework. You can hear this completely. Okay. This is like we are gonna calculate the climate indices. For that, we have particular functions here. We will take this particular function. Each here you can see calculating CDD, CWD, R2ND, like that 5 precipitation indices and 5 temperature indices. So I am running this function. So now this function is defined, and then this is defining the function, just a defining. We haven't executed the code. Then after this, we are doing man-Kendall test. This is the next step, step 5. This was mentioned by Venkatreddy sir in the class at the morning session. Doing like after generating the climate indices value, then we have to do this man-Kendall test to analyze the trends. So I am defining the functions for that also. Here, perform the man-Kendall test. This is We have done this only, like each step by step we have done this under every function. We did this part, we did this part. Now for calculation of the climate indices we have to do this one, and to perform man-canal analysis we should do this part. I'm completely executing this code. This part already we have did it. So I am commenting the code, that's it. So we have defined here the function how to calculate the climate indices. We have defined how to do perform the man-canal analysis. Now we are executing that part of the code. And currently it is running. Next one is spatial interpolation. Here you can see that we are calling this particular function process climate indices, which is given here. Here above we have defined how to calculate each climate indices, 5 precipitation indices and 5 climate indices. Sorry, 5 temperature indices. By calling this function, we are calculating all the indices. Now this is okay. This is showing an error climate indices output. There is no directory. We have to create a directory there. Create a new folder with the same name. That error will be gone. And this will help to save the result to CSV format. This after calculating the climate indices. With this actually this will be calculated from 2010 to 2020. Only 10-year data we are taking, but we have a reference period from 1981 to 2005. We are taking reference data for some calculation of the climate indices. You can see here while calculating R95% and all. Here you can see here 1981 to 2005 we have to take the data for 95%. I am taking as a reference data to compare just for the calculation of the climate indices. Now this is executed. Okay. So we created the folder. Inside that we will get one more CSV folder, CSV. Inside that we can see climate indices has been calculated for each point from 2010 for 10 years to 2020. Look, you can see rainfall points also and temperature points also. Both these are calculated for each 10 indices. CDD, CWD, R20, every values. This will be generated. After that, now we are going to spatially interpret using man-Kendall test. Finding the trend will know the region, how the climate indices is varying. Is it increasing or decreasing? We will get to know. For that, we are using man-Kendall test. So after execution, we can see that also here man killer analysis test. New folder will be created. Inside that we will get one result. There z value, p value and slope is generated. This z value will show if the decreasing trend or increasing trend or no trend for particular rainfall points. Which a region we have taken, that rainfall point is generated, and each CDD CWD is like for each this trend is checked. This trend shows like the significance of whether it is increasing or decreasing. Here you can see if it is like plus, if it is -2, it is a decreasing trend. If it is negative, it is decreasing trend. If it is increasing, it will be positive value, and there is no trend means it will be 0. Okay. The P is defining about the randomness of the value, like how this trend is calculated, how random this trend is calculated, and the slope is how fast this this trend is moving. Like if it is very strong, it is very sudden changes. In slope, it will show how sudden it is changing.
The changes are
High, very high. If the slope is more, the change is very high.
what are the values of P should be the range of P?
The next one is spatial interpolation. With this trend values, and we will get to know the trend in that particular region, and with the help of that we are going to interpolate the data. So we are calling this particular CSV here. You can see that this particular CSV is called here, and we are doing spatial interpolation to get the values in between for that particular region, and we are clipping that region, that particular Hanamokonda region with the help of the shapefile we have uploaded earlier. We will be calling the shapefile here. You can see here, shapefile is called here. Then we are plotting this data. You can see for each precipitation temperature indices, we have taken 10 indices. Temperature 5 temperature indices and 5 rainfall indices. We can see CDD, CWD, R20, RX, all these values. You can see here, look, this is consecutive frost days. In Hanamokonda region, there is no cold climate. So it is having no trend. It is 0. The trend is 0. That's why that area is not having any color change. If it is a frost, if it is a cold region, it would have shown a change. Then finally we are visualizing this. This is just for visualization of these rasters which we have saved. Here we have generated some rasters here, clipped to the region that we will be visualizing here. This is a code which is more dense, but here you can see for the Hanamokonda region, if you click on one raster, Venkata Reddy sir have already specified on this. If you click on a raster, we will get all the 10 indices values. CDD, CWD, you can see that. For each pixel, it will show these values, 10 indices. This is the final visualization part. This can be done in QGIS also. This is done directly in Python. This can be done in QGIS also. This is the complete steps. You can try. I have provided even the file IPYV, like the Jupyter Notebook file directly in my Drive link. You can access in that Drive link and you can download that and you can try that also.
I think it's about the time for ending today's session, but I just want to make this announcement that the last three steps that Surya was showing just now, what you can do is to try on your own if you haven't finished yet. But the only challenge is if you have worked with this laptop or desktop here, it may not be possible for you to continue tomorrow. Or when you have break after lunch, if you want to come and start working on them before we start our session 3, tutorial 3 session, which is a different thing, Snap software that we introduced in QGIS. If you want to continue, since you remember all the steps that what she told you today, that's a possibility if you have used the desktop here. If you have your laptops and want to continue at home this evening, please do it. In any case, if you have not finished, what we can do on Thursday afternoon, first half an hour we will finish with all of you continuing here with Surya's input because she is not here tomorrow. But then the fourth session with HHMS we will start on Thursday afternoon. right after finishing this one. But we will not spend too much time on this. If you want to finish, yourself, I think it will be better. But if you need help and if you want to really completely learn this stuff with our help, I think if you think that's a better idea, please wait until Thursday. We will finish and then move on to the next one. Okay? Is it possible? Is it okay that you can try first, and if there is an issue, then we will, redo it quickly. That way we will save time. Okay? So we can stop here for today because it's about the time now. But we will meet tomorrow at 9:30 in the morning. Okay? Good evening, all of you.
Right? 15,